Teleportation, an idea straight out of science fiction. But is it possible? Could we one day step into a machine and instantly appear somewhere else, light years away or just across the room? For centuries, humans have dreamed of bypassing the limitations of physical space. From the magical portals of fantasy novels to the sleek teleporters in futuristic films, this concept has captivated our imagination. But behind the fiction, scientists have been asking a very real question. Can teleportation actually happen in the physical world? Today, we'll dive deep into the fascinating world of teleportation. From the fundamentals of quantum mechanics to the cutting-edge breakthroughs happening in labs right now, we'll explore if human teleportation could move from fantasy to reality. The journey begins by understanding what teleportation truly is. In simple terms, it's the transfer of matter or information from one place to another without physically traveling through space. But can something as complex as a human body, or even the mind, be teleported? To answer that, we need to look at quantum mechanics, a field of physics that deals with the smallest particles in the universe. Here, particles behave in ways that seem impossible under the rules of classical physics. And at the heart of this is quantum entanglement, a phenomenon that many believe could be the key to teleportation. Quantum entanglement, often called spooky action at a distance, allows particles to be instantaneously connected, no matter the distance between them. If one particle is altered, the other reacts in the same way, faster than the speed of light. Sounds a bit like teleportation, right? In fact, scientists have already achieved quantum teleportation. But before you get too excited, it's important to understand what this means. This type of teleportation doesn't involve physically moving objects or people. Instead, it transfers the quantum state of one particle to another with the help of entanglement. While groundbreaking, we're still light years away from teleporting humans. Now imagine the complexity of teleporting a human being. Every atom, every molecule, and even the electrical impulses in the brain would have to be perfectly replicated somewhere else. The amount of data required is almost beyond comprehension. Then comes the question, would the teleported you be the same you, or just a perfect copy? As we continue to push the boundaries of quantum physics, the ethical, philosophical, and technological challenges of teleportation loom large. But the pursuit of teleportation isn't just about traveling across the galaxy. It could revolutionize communication, computing, and even the way we perceive reality. So, how close are we to realizing this age-old dream? Let's dive into the history, science, and future of teleportation to find out if it's just a sci-fi fantasy, or if teleportation could one day become a part of everyday life. Teleportation as a concept in literature dates back further than many might expect. Some of the earliest stories featured characters disappearing in one place and reappearing in another, often through magical means. These early works laid the foundation for the teleportation fantasies we see today. In the 19th century, writers began experimenting with the idea of instant transportation in more scientific ways. Jules Verne, for instance, explored advanced technologies, hinting at possibilities that were far beyond the realm of his time. Though not strictly teleportation, his vision sparked interest in futuristic travel. As the genre of science fiction emerged, teleportation became a common theme. Writers like H.G. Wells introduced ideas that combined science with the supernatural, blending fiction with elements of theoretical possibility. These stories often featured machines that could move people or objects without traditional travel. One of the most notable early mentions of teleportation came in the form of beam-me-up style devices in serialized fiction. These early depictions were often vague, leaving the mechanics of teleportation to the imagination. The focus was on the mystery and excitement of instant movement. By the mid-20th century, teleportation was a familiar idea in pulp science fiction. Authors like Isaac Asimov and Arthur C. Clarke began to speculate more seriously about the scientific principles behind it. Their stories, while imaginative, often hinted at real scientific questions that remain relevant today. Instead, they focused on the wonders and perils of such a power. Characters would often face moral dilemmas or unforeseen consequences, adding depth to the teleportation trope. Teleportation also appeared in fantasy literature, though often disguised as magic. In these stories, wizards and sorcerers would vanish from one location and reappear elsewhere. While the method was magical, The effect was essentially the same as the teleportation we dream of today. The fascination with teleportation in fiction reflects humanity's desire to overcome the limitations of space. Whether through science or magic, writers have long explored the idea of breaking free from the physical constraints of the world. This longing speaks to a fundamental human curiosity about what might be possible in the future. As the 20th century progressed, the idea of teleportation became more sophisticated in literature. Writers started to consider the implications of data transfer, matter conversion, and the speed of light. These stories began to align more closely with the emerging field of quantum mechanics. Interestingly, many early teleportation stories focused on the impact of instant travel rather than its mechanics. Characters grappled with the consequences of moving from one place to another without time passing. This theme continues to resonate in modern teleportation narratives. Teleportation's early literary history helped shape the public's understanding of the concept. As science progressed, so too did the sophistication of teleportation in fiction. Writers were no longer content with vague explanations and began to tackle the deeper scientific questions. These early literary mentions laid the groundwork for the scientific exploration of teleportation we see today. Fiction allowed readers to dream, and in turn, it inspired scientists to look for ways to turn those dreams into reality. Teleportation truly entered the mainstream with the rise of science fiction in movies and television. One of the most iconic examples is Star Trek's transporter, which became a symbol of instant travel. The phrase, "Beam me up, Scotty," is forever etched in popular culture. In Star Trek, teleportation was depicted as an efficient and seamless way to travel across space, avoiding the need for shuttles or long voyages. The visual effect of characters dematerializing and reappearing instantly added to the wonder. It gave audiences a glimpse of a future where distance was no longer a barrier. The Star Trek transporter wasn't just a narrative tool, it was also a cost-saving measure. Instead of filming elaborate landing scenes, characters could simply beam down to new worlds. This practical decision had an unintended consequence. Teleportation became a staple of futuristic travel in science fiction. Another significant portrayal of teleportation comes from The Fly, where the technology is explored from a darker angle. In this film, teleportation goes horribly wrong, leading to terrifying consequences. It highlighted the potential dangers of trying to manipulate matter at such a fundamental level. The Fly brought a sense of realism and fear to teleportation, showing that even advanced technology could lead to catastrophic results. The gruesome transformation in the movie serves as a cautionary tale, contrasting with the optimistic depictions in other shows. It showed that teleportation, if possible, might come with serious risks. In the world of superheroes, teleportation is often portrayed as a power rather than a technological achievement. Characters like Nightcrawler from X-Men use teleportation as a natural ability, moving instantaneously from one place to another. This adds a fantastical element to the concept, making it more about superhuman capability than science. Nightcrawler's teleportation is visually striking, emphasizing the dramatic and unpredictable nature of such an ability. His sudden bursts of movement and the mysterious smoke left in his wake make the power feel almost magical. These representations tend to focus less on the mechanics and more on the action. Movies like Jumper took teleportation in a different direction, exploring what it would be like to have this ability in a modern setting. The film depicts a world where a select few can teleport at will, using it to escape danger or live lavish lifestyles. This gave a more grounded but still thrilling take on teleportation. Teleportation also plays a key role in the film series Harry Potter, where wizards use a form of teleportation called apparition. Though magical in nature, the effect is much the same. Individuals disappearing from one spot and reappearing elsewhere. Apparition is portrayed as a common but tricky skill, with the risk of splinching adding an element of danger. Even in animated series like Dragon Ball, teleportation appears, often as a technique to outmaneuver opponents. Instant transmission, as it's called, allows characters to teleport across great distances in the blink of an eye. It's often used in battles to gain an upper hand, demonstrating the tactical advantages of teleportation. In Doctor Who, teleportation is seen through various alien technologies, such as the TARDIS's ability to dematerialize and rematerialize in different locations. While technically time travel, it functions similarly to teleportation in its instantaneous relocation of the Doctor and companions. It adds to the sense of limitless exploration the show is known for. These iconic depictions across film and television have shaped how we imagine teleportation, blending science, magic, and the unknown. While each portrayal brings its own spin, they all tap into our desire for freedom from physical limits. Teleportation has always captured the public's imagination in ways few other technologies have. The idea of instantly moving from one place to another feels like a kind of ultimate freedom, defying the natural laws that govern our lives. It's no wonder people are fascinated by it. As teleportation became more prominent in popular media, it began to shape how people thought about the future. For many, teleportation became a symbol of advanced technology, a marker of the kind of world we could only dream about. Its presence in science fiction helped build a collective vision of what humanity might achieve. Even outside of fiction, teleportation started to represent the pinnacle of convenience. In a world where time is a precious resource, the ability to teleport would revolutionize daily life. It allowed people to imagine a future where long commutes and tedious travel could be a thing of the past. The fascination with teleportation also sparked curiosity about the real science behind it. Popular media led people to question whether such technology could ever exist, and many started exploring scientific explanations for what had once seemed purely fantastical. This crossover between fiction and reality drove interest in fields like quantum physics. Teleportation's appeal lies in its simplicity and its mystery. On the surface, it's easy to understand the desire for instant travel, but the deeper complexities of how it might work remain elusive. This balance between the accessible and the unknown keeps people intrigued. Throughout the years, teleportation has become a metaphor for the future itself, always out of reach, yet endlessly pursued. People use it to imagine what life could be like if we could transcend the limitations of time and space. It's a concept that opens up a world of possibilities, both literal and metaphorical. It's not just the science enthusiasts who find teleportation compelling. The general public has embraced it as a staple of futuristic thinking, whether it's in conversations about technological advancement or casual daydreams. Teleportation is often used as shorthand for cutting-edge innovation. The influence of teleportation in media extends beyond entertainment, subtly shaping expectations about what might one day be possible. It fuels a sense of optimism about the future, making people believe that if teleportation can be imagined, it might someday be achieved. This kind of thinking encourages broader exploration of new technologies. This influence also extends into the realm of art and philosophy. Teleportation challenges our fundamental understanding of identity, movement, and existence, prompting questions about what it means to be in a particular place. These questions spark new ways of thinking about human experience and connection. As teleportation permeated popular culture, it began inspiring real-world scientists and innovators. The dream of overcoming distance has motivated some of the greatest minds in physics and engineering. While the technology doesn't exist yet, the public's fascination with it continues to drive the desire to make the impossible possible. It's this blending of imagination and scientific curiosity that makes teleportation such a unique concept. The public's ongoing interest in teleportation helps keep it alive as a serious subject of inquiry, not just a fictional trope. It keeps pushing the boundaries of what we think could one day be real. Teleportation may still be a distant dream, but its presence in the public imagination ensures it remains part of the conversation about the future. It gives people a way to think beyond the present, to envision a world where technology fundamentally reshapes human life. One of the earliest key figures in fictional teleportation is the crew of Star Trek's USS Enterprise. Captain Kirk and his team popularized the concept with their routine use of the transporter, making teleportation seem almost mundane in their futuristic world. This was one of the first times teleportation was presented as a practical, everyday technology. Gene Roddenberry, the creator of Star Trek, played a crucial role in establishing teleportation as a mainstay of science fiction. His vision of a future where technology-enabled instant travel helped cement the transporter as a symbol of advanced civilization. It was a defining element of his imagined universe. Then there's the character of Seth Brundle in David Cronenberg's The Fly. Brundle's teleportation experiments push the boundaries of science fiction into horror, showing how things can go horribly wrong. His tragic transformation offers a darker, more cautionary perspective on the potential dangers of teleportation. Isaac Asimov, one of the most influential science fiction writers, also explored teleportation in his stories. While known for robots and space exploration, Asimov often used teleportation as a narrative tool, emphasizing the ethical dilemmas and scientific challenges it could present. His works influenced generations of writers to consider the deeper implications of such technology. In the world of superheroes, Nightcrawler from the X-Men series stands out as one of the most iconic teleporters. His ability to bamf in and out of spaces made him a fan favorite, showing teleportation not as a scientific achievement, but as a personal power. His unique abilities made teleportation feel dynamic and exhilarating. Arthur C. Clarke, another science fiction giant, explored teleportation in more philosophical terms. His works often questioned humanity's role in a universe where such powers might exist, blending teleportation with themes of higher intelligence and evolution. Clarke's influence on the genre cannot be overstated. Harry Potter introduced millions of readers to Apparition, the wizarding world's version of teleportation. Characters like Dumbledore and Harry use this magical form of travel to great effect, showing that teleportation doesn't need to be rooted in science to capture the imagination. J.K. Rowling's magical twist on the concept brought teleportation into the realm of fantasy for a new generation. In the film Jumper, David Rice is a key figure whose ability to teleport anywhere instantly makes him both powerful and vulnerable. This character brought teleportation to a more grounded modern setting, exploring what it would be like to have such abilities in the real world. His actions raise questions about power, responsibility, and freedom. Kurt Vonnegut also touched on teleportation in his satirical novel, Slaughterhouse-Five. The character Billy Pilgrim becomes unstuck in time, and while not a direct teleporter, experiences disjointed movement through time and space. Vonnegut used this as a metaphor for the randomness and chaos of life, presenting teleportation as a vehicle for exploring deeper themes. Dr. Manhattan from Watchmen presents yet another take on teleportation. His near-godlike powers include the ability to disassemble and reassemble matter, moving himself effortlessly through space. He represents the ultimate expression of teleportation, as his abilities challenge the boundaries of both science and humanity. In Dragon Ball, Goku's instant transmission technique adds a new level of excitement to teleportation in action-packed combat scenes. He uses it strategically in battle, showing how teleportation can be more than just travel. It can be a powerful tool for survival and strategy. The portrayal of teleportation through these key figures reflects the evolving relationship between humans and technology. Each character, from Starfleet captains to comic book superheroes, adds a new layer to how teleportation is viewed in fiction, shaping the way we continue to imagine its possibilities. As science fiction evolved, so did the way teleportation was portrayed. In the early years, it was often a magical or unexplained phenomenon, existing simply as a plot device. It wasn't until the mid-20th century that the idea of teleportation became more grounded in science. The 1960s and 70s saw a shift toward technology-based teleportation, reflecting society's growing interest in space exploration and technological advancements. Teleportation became linked with scientific progress, a symbol of humanity's potential to conquer the vastness of space. It was no longer just a convenience, but a representation of futuristic achievement. In the 1980s and 90s, the darker side of teleportation began to emerge. Films like The Fly introduced audiences to the risks and horrors that could accompany such technology. The idea of teleportation as a dangerous, even destructive process began to take root, as stories explored the potential consequences of tampering with the fabric of matter. By the late 90s and early 2000s, teleportation took on a more personal and psychological dimension. Characters who could teleport were often isolated or alienated, as seen in films like Jumper. The ability to teleport started to raise questions about identity, control, and what it means to belong somewhere. Superhero films of the 21st century often portrayed teleportation as a tactical or combat advantage. Characters like Nightcrawler and Goku used it to outmaneuver opponents, showing teleportation as a dynamic, action-driven ability. It became less about travel and more about power and strategy in high-stakes situations. As technology in the real world advanced, teleportation in fiction began to reflect concerns about data, information, and security. Stories started exploring the idea of teleporting not just physical bodies, but information and digital identities. This reflected society's increasing dependence on technology and the risks of losing control over it. More recently, teleportation has also been used to examine themes of globalization and interconnectedness. In a world where communication and travel are instantaneous, teleportation has become a metaphor for our shrinking global boundaries. It poses questions about the implications of a world without physical distance. In modern science fiction, teleportation has also become more closely associated with virtual reality and digital worlds. The lines between physical and digital teleportation have blurred, with characters often moving between real and virtual spaces seamlessly. This shift mirrors our growing immersion in digital environments. Another emerging theme is the ethical implications of teleportation. Recent stories delve into the morality of duplicating matter, raising questions about the nature of existence and the potential for exploitation. These narratives challenge the assumption that teleportation would be purely beneficial. In the context of space exploration, teleportation remains a hopeful symbol of humanity's potential to transcend vast distances. However, stories are increasingly realistic about the challenges and limitations of such technology. The optimistic visions of early science fiction are tempered by a more nuanced understanding of the complexities involved. Teleportation has also become a way to explore environmental themes, particularly in stories that imagine a future where teleportation replaces traditional forms of transportation. The potential for reducing carbon footprints and resource consumption has entered the conversation, making teleportation part of the dialogue on sustainability. Over time, teleportation has evolved from a simple plot device into a complex, multifaceted concept. Its themes have shifted in response to societal changes, scientific developments, and new philosophical questions. Each era of storytelling has added new layers to our understanding of what teleportation could mean for the future. Quantum mechanics is the branch of physics that deals with the behavior of particles on the smallest scales imaginable. At this level, the rules that govern the everyday world don't seem to apply. Particles behave in ways that are strange and often counterintuitive. One of the key principles of quantum mechanics is superposition. This concept suggests that particles can exist in multiple states at once, only settling into a single state when observed. It's a phenomenon that challenges our traditional understanding of reality. Another foundational idea is quantum entanglement, often described as spooky action at a distance. When two particles become entangled, the state of one is instantly connected to the state of the other, no matter how far apart they are. This defies the classical idea that information can only travel at the speed of light. The uncertainty principle is another core concept. It states that you can never precisely know both the position and momentum of a particle at the same time. The more you know about one, the less you know about the other. This uncertainty is a fundamental feature of the quantum world. Wave-particle duality is another strange aspect of quantum mechanics. Particles like electrons can act both as particles and as waves, depending on how they are observed. This duality adds to the mystery of how matter behaves on such a small scale. Quantum mechanics also introduces the concept of probability. Unlike classical physics, which deals in certainties, quantum mechanics operates in terms of likelihoods. We can only predict the probability of a particle being in a certain place or state at any given time. The concept of quantum states is crucial for understanding teleportation. A quantum state contains all the information about a particle, and this information can, in theory, be transferred from one particle to another. This is where quantum teleportation becomes a possibility. Quantum teleportation relies on the principles of entanglement to transfer the quantum state of one particle to another without physically moving the particle itself. It's important to note that this isn't about moving matter, but rather about transferring information. Measurement plays a crucial role in quantum mechanics. Observing or measuring a quantum system collapses its superposition, forcing it to settle into a specific state. This interaction between the observer and the observed is one of the most puzzling aspects of quantum theory. Quantum decoherence explains why we don't see quantum effects on a large scale. When a quantum system interacts with its environment, it loses its quantum properties, behaving more like the classical world we're familiar with. This is one reason why teleportation at the macroscopic level remains so challenging. In recent decades, quantum mechanics has led to the development of technologies like quantum computers and quantum cryptography. These applications are pushing the boundaries of what we can do with quantum theory, and they hold the key to unlocking future advancements, including the possibility of teleportation. Despite its complexity, quantum mechanics is one of the most well-tested theories in science. It's been confirmed through countless experiments, yet it continues to challenge our understanding of reality. This strange, invisible world may hold the answers to whether teleportation will ever be possible. Quantum entanglement is one of the most mysterious and fascinating phenomena in quantum mechanics. When two particles become entangled, their properties become linked in such a way that the state of one instantly affects the state of the other, no matter how far apart they are. This connection remains, even if the particles are separated by vast distances. What makes entanglement so strange is that it seems to defy the laws of classical physics. Information appears to travel between the particles faster than the speed of light, something that should be impossible according to Einstein's theory of relativity. This spooky action at a distance baffled even Einstein himself. Entanglement doesn't just mean the particles share some common property. It means their states are fundamentally interconnected. If one particle's spin is measured, the other particle's spin will be the opposite instantly, regardless of the distance between them. It's as if the two particles are communicating in real time. However, this instant connection doesn't involve any transfer of information in the traditional sense. It's not like sending a message from one particle to another. Instead, the particles are behaving as a single system, no matter how far apart they are. This is what makes quantum entanglement so unique. Now, quantum entanglement is at the heart of quantum teleportation. In teleportation experiments, entanglement allows the transfer of quantum information from one particle to another without the particles physically interacting. This process relies on the unique properties of entangled particles to send information about a particle's quantum state across space. When two particles are entangled, measuring one instantly tells you something about the other. This happens without any need for a signal to be sent between them, making it an essential component in the idea of teleporting quantum states. It's not about moving matter, but rather about transferring the information that defines the state of matter. In practical terms, creating entangled particles is no small feat. It requires carefully controlled conditions and precise manipulation of quantum systems. But once entanglement is established, it opens up possibilities for quantum communication, quantum computing, and theoretically, teleportation. Despite its strangeness, quantum entanglement has been experimentally proven many times over. In the lab, scientists have successfully entangled photons, atoms, and even small molecules. These experiments have shown that entanglement is real and that its effects can be reliably observed and measured. But entanglement isn't just limited to teleportation. It plays a crucial role in quantum cryptography, where it's used to create secure communication channels, because any attempt to measure or interfere with entangled particles would disrupt the system. Entanglement-based communication is theoretically unbreakable. One of the biggest challenges with entanglement is maintaining it over long distances. While scientists have successfully entangled particles over several kilometers, scaling this up to much greater distances is a major hurdle. Yet overcoming this barrier could be key to developing global quantum networks. Quantum entanglement also raises deep philosophical questions. If two particles can influence each other across vast distances instantaneously, what does that say about the nature of reality? Are there hidden connections in the universe that we don't yet understand? These questions remain at the cutting edge of both physics and philosophy. As we learn more about entanglement, it continues to reshape our understanding of the quantum world. It's a strange, almost magical phenomenon, but it's also the foundation of some of the most advanced scientific research happening today. Its role in teleportation is just one part of the larger puzzle. Teleportation would fundamentally change the way we think about travel. Traditional travel, whether by car, plane, or spaceship, involves moving through space and time, navigating physical obstacles and distances. Teleportation, on the other hand, bypasses these limitations entirely. In traditional travel, time is always a factor. No matter how fast we move, it still takes time to get from one place to another. Even at the speed of light, it would take years to travel between stars. Teleportation could potentially eliminate that time, allowing instantaneous movement from one location to another. Another difference is the energy required. Traditional travel consumes vast amounts of energy, especially over long distances. Planes burn fuel, cars use gasoline or electricity, and space travel requires enormous amounts of power. Teleportation, if achievable, might use energy in entirely different ways, possibly making long-distance travel more efficient. With traditional travel, physical wear and tear is inevitable. Whether it's the toll on machines, human bodies, or the environment, moving through space takes a toll. Teleportation, by contrast, could eliminate these physical stresses, making travel not only faster, but potentially less damaging to people and the planet. Safety is a major concern in traditional travel. Airplane crashes, car accidents, and spacecraft malfunctions all pose serious risks. If teleportation became a reality, it could eliminate many of these dangers by removing the need for physical vehicles and infrastructure. However, teleportation comes with its own set of challenges. Traditional travel is well understood, with systems in place for navigation, safety, and logistics. Teleportation, especially on a large scale, would require entirely new systems and safeguards to ensure it worked reliably and safely. There's also the question of accessibility. Traditional travel is increasingly becoming available to more people, thanks to advancements in technology and infrastructure. But teleportation might be so complex or energy-intensive that it could remain an exclusive technology, at least in its early stages. When we travel traditionally, we experience the journey itself, often passing through different environments and cultures. Teleportation would remove that experience, making travel instantaneous but possibly disconnecting people from the physical act of moving through space. This could change how we perceive distance and location. Teleportation could revolutionize industries reliant on transportation, such as shipping and logistics. Goods that currently take days or weeks to transport could arrive instantly. This would upend global trade and have massive implications for economies around the world. But teleportation might also have unforeseen social impacts. Traditional travel often creates natural barriers between places, creating a sense of distance and separation. With teleportation, those barriers would disappear, potentially reshaping how societies function and interact. Environmental impacts are another key consideration. Traditional travel, especially air and space travel, contributes to pollution and environmental degradation. Teleportation could, in theory, provide a greener alternative by eliminating the need for fuel-burning vehicles. In the end, teleportation wouldn't just be a new way to travel, it would completely redefine our relationship with space, time, and movement. Traditional travel as we know it today would become obsolete, replaced by a future where distance might no longer matter. Theoretical foundations in physics offer some of the most compelling insights into how teleportation could work. One of the primary ideas comes from quantum mechanics, particularly the concept of quantum entanglement, which suggests that particles can be linked across vast distances. This connection opens up the possibility of transferring information instantaneously. Quantum teleportation is built on the idea of transferring the quantum state of a particle to another particle without physically moving the particle itself. This isn't teleportation in the traditional sense, but rather a way of recreating the exact quantum information elsewhere. It's a fundamental leap from how we normally think of moving objects. In classical physics, the idea of teleportation is much harder to justify. Newtonian mechanics deals with objects moving through space, not vanishing from one place and reappearing in another. The challenge lies in reconciling our understanding of the physical world with the possibilities presented by quantum theory. Relativity also plays a role in how we think about teleportation. According to Einstein's theory of relativity, nothing can travel faster than the speed of light. But teleportation might bypass this limitation, transferring information instantaneously without breaking the rules of relativity. This raises questions about the nature of space and time. One of the key issues with teleporting physical objects is the vast amount of information involved. To teleport a human, for instance, you would need to capture and transfer every detail about every atom in the body. This level of precision is beyond our current technology, but in theory, it could be possible with advances in data storage and computation. In physics, the concept of wave-particle duality also plays a role in understanding how teleportation might work. If particles can behave like waves, then perhaps we could use this property to transfer their information across space. It's an idea that challenges the traditional view of matter as fixed and immovable. Teleportation, as theorized in physics, doesn't violate the laws of conservation. The information about the particles is transferred, not the particles themselves, so the total amount of matter and energy in the universe remains constant. This theoretical understanding helps ground teleportation in established scientific principles. The idea of wormholes is another theoretical concept that ties into teleportation. In theory, a wormhole could act as a shortcut through space-time, allowing for near-instantaneous travel between two distant points. While still speculative, wormholes represent one of the few potential mechanisms for teleportation on a larger scale. Quantum field theory also offers insights into how teleportation could work. According to this theory, particles are excitations of underlying fields that exist everywhere in space. By manipulating these fields, it might be possible to recreate particles in different locations, effectively achieving teleportation. The no-cloning theorem in quantum mechanics presents a significant challenge. It states that an exact copy of a quantum state cannot be made. This means that teleportation would involve transferring the original state and destroying it at the source, raising profound questions about identity and continuity. Theoretical physicists also explore the possibility of teleportation through advances in quantum computing. Quantum computers could process the massive amounts of data required for teleportation, making it theoretically possible to manipulate quantum information in ways we can't yet achieve with classical computers. Despite the complexities, the theoretical foundations in physics provide a framework for exploring teleportation as more than just a fantasy. These ideas push the boundaries of what we understand about the universe, offering tantalizing possibilities for how teleportation could one day become reality. One of the biggest challenges in understanding teleportation scientifically is the sheer complexity of the human body. Every atom, every molecule would need to be mapped and transmitted perfectly for successful teleportation. The amount of information required is staggering, far beyond what current technology can handle. Even if we could capture all this information, we would then face the issue of transmitting it. How do you send this vast amount of data instantaneously, and where does it go? The science of transmitting physical information across space remains one of the most daunting obstacles. Quantum mechanics provides a theoretical framework for teleportation, but it's notoriously difficult to work with in practice. The behavior of particles on a quantum level is unpredictable, and even small changes in conditions can disrupt the process. Maintaining control over quantum systems long enough to teleport them remains a major hurdle. Another scientific challenge lies in preserving the integrity of the original object during teleportation. The process would involve breaking down matter at one location and reconstructing it at another. Ensuring that no information is lost or altered along the way is crucial, but difficult to guarantee with current technologies. Decoherence is a significant problem in teleportation experiments. In quantum mechanics, a system needs to remain isolated from its environment to maintain its quantum properties. But in the real world, perfect isolation is nearly impossible, and any interaction with the environment can cause the system to lose its quantum state. There's also the issue of entanglement, which is crucial for quantum teleportation. While scientists have successfully entangled particles over short distances, maintaining entanglement over longer distances, especially on a scale large enough to teleport complex objects, remains a significant technical challenge. Another major challenge is the energy required for teleportation. Moving even small amounts of matter or transferring large amounts of information demands an enormous amount of energy. Scaling this up to teleport larger objects, like humans, could require more energy than we can currently produce. There's also a philosophical question that scientists grapple with. If you teleport a person by breaking them down and reconstructing them elsewhere, is the person at the destination really the same as the original? This raises deep questions about identity, consciousness, and the nature of existence. Errors in teleportation would be catastrophic. Even a tiny mistake in the reassembly process could lead to serious consequences, from physical deformities to complete failure. The margin for error in teleportation is practically zero, making it an incredibly difficult process to perfect. In traditional transportation, we understand the physics of movement through space. But teleportation, by its nature, bypasses the familiar rules of movement. Scientists are still grappling with how to make sense of teleportation in a way that fits within our current understanding of the laws of physics. Teleporting information at the quantum level doesn't mean you can teleport matter. The process transfers quantum states, not physical objects, and turning those states back into matter is something we don't yet know how to do. This gap in our understanding is one of the biggest obstacles to achieving teleportation as we imagine it. The concept of teleportation touches on many different fields: quantum physics, computing, data transfer, and even biology. Each presents its own set of challenges, and integrating them into a cohesive system is far beyond what current scientific understanding allows. The pieces are there, but we haven't yet figured out how to put them together. The data complexity involved in human teleportation is staggering. Every single atom in the human body would need to be mapped, recorded, and transmitted with perfect accuracy. This includes not just the physical structure, but also the quantum states of each particle. There are approximately 37 trillion cells in the human body, and each cell contains billions of atoms. Capturing all of this information would require processing and storing data on an unimaginable scale. This is far beyond the capabilities of our current technology. On top of that, it's not just about atoms. You'd also need to account for the subatomic particles, protons, neutrons, and electrons, and the quantum states they occupy. Quantum states are delicate and can change rapidly, so capturing them in a way that preserves their accuracy adds another layer of complexity. The brain alone presents enormous challenges. Neurons are constantly firing, and their connections form the basis of consciousness, memory, and personality. Teleporting a person would mean replicating not just the structure of the brain, but the exact state of all its neural activity at the moment of teleportation. Furthermore, DNA sequences in every cell carry critical genetic information. Even the slightest error in replicating DNA during teleportation could have catastrophic effects, leading to mutations or loss of vital biological functions. The precision needed is unimaginable. Current data storage technologies would be utterly insufficient for this task. The amount of data required to fully describe a human body would exceed the storage capacity of all the data centers on Earth. We would need entirely new methods of data storage and transmission to make this feasible. The speed at which this data must be transmitted also poses a huge challenge. For teleportation to feel instantaneous, all of this information would need to be sent and reconstructed in fractions of a second. Transmitting this vast amount of data quickly and without loss is beyond anything we can currently achieve. Even if we could capture and transmit the necessary data, reassembling it accurately would be an equally monumental task. Rebuilding a human being atom by atom, in exactly the right configuration, would require incredibly precise technology. Any slight misalignment could result in disastrous consequences. Additionally, the Heisenberg uncertainty principle in quantum mechanics states that we cannot know both the position and momentum of a particle with perfect accuracy. This fundamental limitation makes it theoretically impossible to measure every particle in a human body with the precision required for perfect reconstruction. Errors in the data transfer could lead to irreparable damage. A small glitch in the teleportation process might result in missing or incorrect information, leading to incomplete or malfunctioning reconstructions. The risk of such errors would be immense without a flawless error correction system in place. Moreover, there's the issue of biological systems being dynamic, constantly in motion and change. Capturing a snapshot of the body at one moment might not be enough. Teleporting a living being means accounting for processes like heartbeat, digestion, and neural firing, all of which are in constant flux. In the end, the data complexity involved in teleporting a human being is one of the biggest scientific challenges. It's not just a matter of gathering enough information, but also ensuring that it can be transmitted and reconstructed with absolute fidelity, a task far beyond our current capabilities. The energy requirements for teleportation would be astronomical. To break down and reconstruct a human body at the atomic level would require an immense amount of energy, far more than we currently have the ability to produce or manage efficiently. This is one of the most significant obstacles to making teleportation a reality. Just separating the bonds between atoms in a human body would require vast amounts of energy. Every single bond between the atoms that make up your body would need to be broken and reassembled perfectly. The energy needed to do this safely and quickly is far beyond anything achievable with modern technology. Transporting the data involved in teleportation would also demand a massive energy infrastructure. Transmitting the quantum information for trillions of atoms would require a system that can handle huge amounts of power and do so without any delays or interruptions. Energy efficiency would need to be drastically improved. Even if you could generate enough energy, you would need a way to harness and control it with precision. The energy must be applied carefully to avoid damaging the body or altering its structure in any way. Current technologies simply don't have the level of control necessary to manage that amount of power safely. Another challenge lies in sustaining that energy over time. Teleporting a complex system like a human being isn't instantaneous in the sense that the process could require energy to be applied continuously during deconstruction, transmission, and reconstruction. Maintaining that energy flow without any disruption is another hurdle. The process of creating and maintaining quantum entanglement, which is essential for teleportation, also requires energy. While the particles themselves may not consume energy, the equipment needed to create and preserve entanglement does. As the scale increases, so too does the energy demand to maintain stable quantum states. Moreover, you would have to factor in the energy required for classical communication. After the quantum state is teleported, classical data must still be sent to finalize the process. This involves not just transmitting information, but ensuring the infrastructure for this communication operates seamlessly. The laws of thermodynamics present another problem. Breaking down and rebuilding matter involves massive amounts of entropy, which would need to be carefully managed. Overcoming this increase in disorder requires energy, further adding to the overall requirement for teleportation to succeed. There's also the issue of energy losses. In any real-world system, some energy is inevitably lost as heat. In teleportation, where precision is critical, even small energy losses could cause errors in the process. Finding a way to minimize or eliminate these losses would be essential to ensure the accuracy of the teleportation. Current estimates for the energy required to teleport even small objects are staggering. Some calculations suggest that the energy needed to teleport just a few atoms would rival the total energy output of a power plant. Scaling that up to a human being would require advances in energy production that we've only begun to imagine. The energy problem is not just about production, but also about storage. Even if we could generate enough energy for teleportation, storing that energy in a way that can be released quickly and precisely is another challenge. Batteries and energy storage systems today are nowhere near capable of handling this kind of demand. Ultimately, the energy requirements for teleportation are one of the biggest obstacles scientists face. Without breakthroughs in energy generation, storage, and management, teleportation will remain an impractical, energy-intensive concept far beyond our current reach. Teleportation brings with it a host of ethical and philosophical questions that challenge our very understanding of identity and existence. One of the most pressing concerns is the nature of the self. If a person is broken down into their atomic structure and reassembled elsewhere, is the person who arrives truly the same as the one who left? This question of continuity of consciousness is profound. If teleportation involves destroying the original person and recreating them from scratch, does the original consciousness survive? Or is the new person merely a copy, with the original being effectively killed in the process? The idea of duplication also raises concerns. If the teleportation process could somehow fail to destroy the original, would there be two identical people, each believing they are the same individual? This scenario poses significant ethical dilemmas about identity and individuality. There are also moral questions around consent and safety. If teleportation became a common form of travel, how could we ensure that people are fully informed of the risks, both physical and existential? Would individuals be comfortable with the potential that teleportation could mean the end of their original self? Moreover, the technology could lead to issues of access and inequality. If teleportation is developed but remains costly or difficult to access, it could create new social divides. Who gets to use teleportation, and who is left behind using traditional methods of travel? There's also the potential for misuse. Could teleportation be weaponized, used for criminal purposes, or exploited for illegal surveillance? The ability to move instantaneously or transfer information without detection presents significant concerns for privacy and security. The question of bodily integrity is another important issue. Our bodies are not just collections of atoms. They are living systems with complex biological processes. Teleporting a human would involve breaking apart these systems, raising concerns about whether reassembled bodies would function exactly as they should. Another philosophical issue involves the impact on personal responsibility and accountability. If someone commits a crime and teleports elsewhere, how would laws and justice systems adapt? Would teleportation make it easier to escape responsibility, or could it introduce new forms of identification and tracking? Then there is the question of teleporting individuals with disabilities or medical conditions. Would teleportation maintain all aspects of their physical condition, or could it inadvertently correct certain conditions, raising complex questions about bodily autonomy and identity? Teleportation also challenges our notions of place and presence. In a world where distance no longer matters, how would our relationships with geography, travel, and even the concept of home change? Would teleportation diminish the value of physical location? Finally, the environmental implications must be considered. While teleportation could theoretically reduce the need for fossil fuel-based transportation, the energy requirements for such a technology are immense. Could teleportation, in its quest for convenience, lead to greater environmental harm? These ethical and philosophical questions show that teleportation isn't just a technical problem to solve. It strikes at the heart of human identity, society, and our relationship with the world around us. As scientists work toward making teleportation possible, these deeper concerns will need to be addressed just as seriously as the technological hurdles. The technological limitations of teleportation are vast and complex, spanning multiple fields of science and engineering. One of the most obvious challenges is the lack of technology capable of handling the immense amount of data required to teleport a human being. Even the most advanced computers today cannot process or store the trillions of bits of information needed to map and reconstruct every atom in a person's body. Quantum teleportation, as it currently stands, only works on the level of individual particles like photons. Scaling this up to larger, more complex systems, such as molecules or living organisms, is far beyond our current capabilities. We simply don't have the technology to manipulate and entangle large numbers of particles with the precision needed for teleportation. Another major limitation is the need for quantum entanglement. Creating and maintaining entangled particles over long distances is incredibly difficult, and even the smallest disruption can break the entanglement. This fragility makes teleportation highly unreliable, especially over vast distances. Teleportation also requires classical communication channels to send the measurement data necessary to complete the process. This means that even if the quantum state is transmitted instantly, the overall process still depends on slower, traditional methods of communication. This bottleneck prevents true instantaneous teleportation. The issue of quantum decoherence is another hurdle. Quantum systems are extremely sensitive to their surroundings, and interactions with the environment can cause the quantum state to collapse, making teleportation impossible. Maintaining the isolation needed for quantum teleportation on a large scale is technologically challenging. Furthermore, current teleportation experiments require highly controlled environments with sophisticated equipment, such as vacuum chambers and cryogenic cooling. These conditions are not practical for everyday use, and developing technology that can operate outside of the lab is a long way off. Energy efficiency is another significant limitation. As it stands, the energy required to teleport even small particles is extremely high, and scaling this up to something as complex as a human would require an unimaginable amount of power. Advances in energy production and storage are necessary before teleportation can be considered a feasible option. The precision needed to reconstruct matter exactly as it was before teleportation is another obstacle. Teleportation would require perfect accuracy in reassembling atoms and molecules in their original configuration. Any slight deviation could result in errors that are potentially harmful or even fatal. Technological limitations also extend to error correction. In quantum computing and communication, error correction is an ongoing challenge, and the same would apply to teleportation. Finding ways to detect and correct errors in real time is crucial for the process to work reliably. Another issue is the current lack of infrastructure. For teleportation to become a viable technology, it would require an entirely new network of devices and systems capable of generating, maintaining, and transmitting quantum states over large distances. This infrastructure does not yet exist and would require significant investment and development. Technological advancements in artificial intelligence and machine learning might help manage the complexity of teleportation. But we are still far from creating AI systems capable of handling such immense amounts of data and making real-time decisions during the teleportation process. In the end, the technological limitations of teleportation are vast and interconnected. Progress is being made in fields like quantum computing and communication, but the leap from small-scale experiments to practical human teleportation involves overcoming technological challenges that we are only beginning to understand. Teleportation brings with it numerous biological risks and concerns, many of which remain unresolved. The most obvious is whether a human body can survive the process of being broken down and reassembled at the atomic level. The complexity of the human body, with its delicate systems and intricate biochemical reactions, makes this an enormous challenge. One major concern is the potential damage to DNA. Our genetic material is highly sensitive to changes, and even a small error in reassembling the billions of DNA strands could lead to mutations. These mutations could cause anything from minor health issues to life-threatening diseases. Another issue is the integrity of biological systems. Our organs, tissues, and cells work together in a finely tuned balance. Disrupting these systems during teleportation, even momentarily, could lead to irreversible damage. There's no guarantee that these systems would function normally once reassembled. Teleportation could also have profound effects on the brain. Neural networks are constantly active, and even the slightest interruption in their activity could lead to cognitive problems, memory loss, or even complete loss of consciousness. The risk of disturbing the brain's delicate processes is significant. There's also the concern of continuity of life. If teleportation involves disassembling every molecule in the body, would the person who emerges at the other end be the same individual, or merely a perfect copy? This question has deep philosophical implications, but also biological ones, as it challenges our understanding of life and identity. Even the body's immune system could be at risk. Teleportation might alter or disrupt the immune system, potentially leaving the individual vulnerable to infections or autoimmune disorders. Reassembling immune cells with the same level of precision as the rest of the body is a massive undertaking. Furthermore, teleportation could affect the body's microbiome, the community of microorganisms that live within us and play a vital role in our health. If these microorganisms are not perfectly reconstructed, it could lead to digestive issues, weakened immunity, and other health problems. Cellular regeneration is another concern. Our bodies are constantly repairing and regenerating cells, and interrupting this process through teleportation could cause cells to malfunction or die. This could lead to tissue damage or even long-term health issues that might not be immediately apparent. There are also risks related to the reassembly process. Even the smallest error in reconstructing cells, tissues, or organs could have catastrophic effects. A misaligned artery or a misplaced neuron could result in immediate death or severe disability. The potential for teleportation to disrupt cellular energy processes is another issue. Our cells rely on the constant production and transfer of energy to function. Any interruption in these processes during teleportation could cause cells to lose their ability to produce energy, leading to widespread organ failure. There's also the question of whether teleportation could accelerate aging. The process of breaking down and rebuilding cells might cause them to lose some of their regenerative capacity, leading to premature aging or a shortened lifespan. Ultimately, the biological risks and concerns surrounding teleportation are profound. While the technology may one day become viable, the potential dangers to the human body are significant, and we are far from understanding how to mitigate these risks. When comparing teleportation to warp drives, one of the key differences lies in the mechanics of travel. Teleportation, as imagined, involves instantaneously moving from one point to another by breaking down and reconstructing matter. Warp drives, on the other hand, aim to bend or manipulate space-time, allowing for faster-than-light travel without breaking the laws of physics. Warp drives rely on the concept of creating a bubble around a spaceship, contracting space in front of it and expanding space behind it. In theory, the ship itself doesn't move faster than light, but instead rides this space-time distortion. This allows it to cover vast distances at superluminal speeds without violating the speed of light. Teleportation bypasses the need for any travel at all. Instead of moving through space, it involves the instant transmission of a person or object's quantum information. While warp drives manipulate the fabric of space-time, teleportation focuses on data transfer and reconstruction. In terms of energy requirements, both technologies present significant challenges. Warp drives, like the Alcubierre drive, are theorized to require massive amounts of negative energy or exotic matter, something we have no practical way of producing. Teleportation, as discussed earlier, also requires enormous energy, but in the context of breaking down and transmitting atomic information. Another key distinction is the impact on the traveler. With teleportation, there's the existential risk of losing one's original self or creating a copy, which raises questions about continuity of consciousness. Warp drives, in contrast, involve physical travel without the disintegration of the body, so the person on board would remain intact throughout the journey. Teleportation could theoretically take you anywhere instantly, with no regard for the distance between 2 points. Warp drives, while fast, would still require some travel time, as they don't completely eliminate the need to move through space. However, warp drives have the advantage of allowing for continuous movement through the universe rather than relying on specific quantum links. One major advantage of warp drives is that they don't involve disassembling and reassembling matter. This makes them conceptually safer in terms of maintaining biological integrity. Teleportation, by contrast, has inherent risks in reassembling complex systems like the human body and ensuring they function properly. Warp drives would also allow for more gradual exploration. Instead of instantaneously arriving at a destination, warp travel would give explorers the chance to observe and interact with the space around them. Teleportation, by comparison, would remove any sense of journey or passage. Both technologies are currently theoretical, but warp drives have some grounding in Einstein's theory of general relativity. The mathematical models exist, although the physical requirements remain insurmountable. Teleportation, on the other hand, exists on a small scale in quantum experiments, but scaling it up for practical human travel seems even further away. There's also a question of which technology would be more useful for long-distance space travel. Warp drives could be ideal for traveling between stars or galaxies, allowing ships to traverse vast distances without encountering any significant obstacles. Teleportation might be more practical for short-range travel, provided the technology ever advances to that point. In terms of infrastructure, warp drives would still require traditional spacecraft equipped with the technology to bend space-time, whereas teleportation might one day eliminate the need for physical vehicles altogether. Each approach has its own logistical demands and challenges. Ultimately, teleportation and warp drives represent two very different solutions to the same problem, overcoming the vast distances of space. While both are captivating concepts, each has its own limitations, and we are still far from achieving either in any practical form. The future of space travel may involve one, both, or something entirely different. Hypersonic travel is rapidly advancing, offering the potential to significantly reduce travel times across the globe. While not as instantaneous as teleportation, hypersonic travel could move people at speeds greater than 5 times the speed of sound, or Mach 5. This would make a flight from New York to Tokyo possible in just a couple of hours. The technology behind hypersonic travel relies on cutting-edge developments in aerodynamics and materials science. At such high speeds, the heat generated from air friction becomes a significant challenge. Engineers are working on new heat-resistant materials that can withstand the extreme temperatures experienced during hypersonic flight. One of the most promising advancements in hypersonic travel is scramjet technology. A scramjet, or supersonic combustion ramjet, is an engine that compresses incoming air and ignites fuel at hypersonic speeds, making it much more efficient than traditional rocket engines. This technology is seen as a key to unlocking sustained hypersonic flight. Military applications of hypersonic travel have driven much of the recent progress. Several countries are developing hypersonic missiles capable of evading modern defense systems due to their speed and maneuverability. This research, while primarily for defense, has direct implications for civilian travel technologies in the future. The aerospace industry is also exploring hypersonic airliners for commercial travel. Several companies are designing planes that could operate at hypersonic speeds, drastically cutting travel time between continents. While still in the development phase, these projects show how close we might be to realizing practical hypersonic travel. One of the main hurdles for hypersonic travel is fuel efficiency. At such high speeds, fuel consumption increases dramatically, making it costly and environmentally challenging. Researchers are focusing on improving fuel efficiency and exploring alternative fuels to make hypersonic flight more sustainable. Another challenge is the noise generated by hypersonic aircraft. Sonic booms, caused when planes break the sound barrier, would become a constant issue at hypersonic speeds. Scientists are studying ways to reduce or manage these booms, as public acceptance of this technology will depend in part on minimizing its impact on the environment and communities. The safety of hypersonic travel is another concern. Flying at such high speeds leaves little margin for error, and any malfunction could have catastrophic consequences. Engineers are focused on developing robust safety systems that can detect and respond to issues instantly, ensuring passenger security. While hypersonic travel is still in the early stages of development for commercial use, it could eventually transform how we move around the planet. By cutting long-haul flights from 12 hours to just a couple, hypersonic planes would reshape global transportation, making the world feel smaller and more connected. The potential for hypersonic travel doesn't stop at Earth's atmosphere. Space agencies are also interested in this technology for reaching low Earth orbit more efficiently, potentially making space travel more accessible. Hypersonic craft could serve as a bridge between aviation and space exploration. Governments are investing heavily in hypersonic research, pushing forward the boundaries of what's possible in aviation. With so much momentum, we may see hypersonic passenger flights within the next decade, though widespread use will require solving the technological and regulatory challenges that still exist. In the grand scheme, hypersonic travel represents a middle ground between current air travel and more futuristic ideas like teleportation. While it may not offer the instant travel teleportation promises, it's a step toward radically faster and more efficient ways of moving across the planet and beyond. Space elevators are one of the most ambitious concepts for future space travel, designed to provide a continuous, low-cost method of reaching orbit. The idea involves a tether anchored to the Earth and extending into space, with vehicles capable of climbing it to carry cargo and passengers into orbit without the need for rockets. The key challenge with space elevators is the material needed for the tether. It would need to be incredibly strong yet lightweight enough to support its own weight over tens of thousands of kilometers. Current materials like carbon nanotubes and graphene show promise, but no material has yet been proven to meet all the necessary requirements. If space elevators were built, they could revolutionize access to space. Unlike traditional rockets, which require massive amounts of fuel and produce emissions, space elevators would operate more like cable cars, offering a cleaner, more sustainable way to reach orbit. This could lower the cost of sending both humans and materials into space. Another futuristic concept is the idea of vacuum tube trains, often referred to as hyperloops. These trains would travel through low-pressure tubes at speeds exceeding 1,000 kilometers per hour, reducing air resistance and friction. This could significantly reduce travel times between cities, making long-distance commutes feasible. Vacuum tube trains require advanced infrastructure and technology to maintain the low-pressure environment necessary for high-speed travel. Creating a large network of these tubes would be a major engineering feat, but the potential to revolutionize ground-based travel makes it a compelling vision for the future. Maglev trains, which use magnetic levitation to reduce friction and allow for higher speeds, are another form of futuristic transport already being developed. These trains could complement or even evolve into vacuum tube trains in the future, offering a mix of speed, efficiency, and environmental benefits. Underwater transportation systems, such as submerged floating tunnels, have also been proposed as a way to connect land masses more efficiently. These tunnels could provide fast, direct routes between countries or even continents, potentially reducing the need for air travel. In addition to these earthbound transport systems, space tourism is another futuristic mode of travel that's beginning to take shape. Companies like SpaceX and Blue Origin are working on making space travel accessible to civilians. While still in its infancy, space tourism represents the first steps toward a future where travel between planets could become a reality. Flying cars, long a staple of science fiction, are also moving closer to reality. Advances in electric propulsion and autonomous driving technology are making it possible to envision small, personal aircraft for city travel, potentially alleviating congestion in crowded urban areas. For longer distance travel, airships have been revisited as a potential environmentally friendly alternative to traditional airplanes. With advancements in lightweight materials and renewable energy sources, modern airships could offer low-emission transport for both cargo and passengers. Suborbital flights, which use spacecraft to quickly travel across the globe by briefly entering space, are another concept under development. These flights could cut international travel times down to just a couple of hours, offering a new option for those seeking speed without the complexities of teleportation or warp drives. Each of these futuristic transport concepts faces significant technical, financial, and regulatory challenges, but they represent bold steps toward reimagining how we move around the Earth and beyond. Whether through space elevators, vacuum tube trains, or flying cars, the future of transportation holds possibilities we're only beginning to explore. The time required for developing teleportation, or even some of these other futuristic transport methods, is difficult to predict. For teleportation, we are still in the early stages of understanding the fundamental science. Quantum teleportation of particles is a reality, but scaling that up to complex objects or living beings could take centuries. Development timelines for technologies like space elevators or hypersonic travel are easier to estimate, but still face significant hurdles. Space elevators, for example, depend on material science breakthroughs that might take decades. Even once the materials are available, constructing such a structure would require massive global collaboration and resources. Hypersonic travel is likely to arrive sooner. Military applications are pushing the technology forward, and commercial hypersonic planes could be operational within the next 10 to 20 years. However, perfecting this technology and making it widely accessible will take additional time as safety, cost, and environmental impact are addressed. For warp drives, the timeline is even more speculative. While theoretically possible, the immense energy requirements and need for exotic materials like negative energy make it a distant goal. We might need breakthroughs in fundamental physics before warp drives can move from science fiction to reality, potentially requiring many centuries of development. Space elevators could be feasible within the next 50 to 100 years, depending on advances in materials like carbon nanotubes or graphene. However, constructing a space elevator would be one of the most ambitious engineering projects in history, and the time needed for building it would stretch across decades. Vacuum tube trains, such as hyperloops, are already being tested on a small scale, but building large networks that span countries or continents will take significant time. We might see limited commercial hyperloops within the next few decades, but a fully integrated system could take much longer, perhaps 50 years or more. Flying cars and air taxis are expected to arrive much sooner, with prototypes already being tested. We may see flying cars enter the market within the next 10 to 20 years, though widespread adoption will depend on advancements in battery technology, infrastructure, and regulatory approval. Space tourism, on the other hand, is already beginning. Companies like SpaceX and Blue Origin are launching suborbital flights, and the next decade will likely see more civilian missions to space. Expanding this into regular travel to the Moon, Mars, or beyond, however, will take several decades of continued development and investment. Underwater transportation systems like submerged floating tunnels are still in the conceptual stage, with no significant prototypes in development. Creating these systems will likely take many decades, as the engineering challenges are immense. If pursued, we might not see these until the latter half of the century. For maglev trains, we're already seeing operational systems in countries like Japan, but expanding these to more regions and pushing the technology further will take time. Full adoption in major countries could take another 20 to 40 years, depending on investment in infrastructure and public demand. Suborbital flights for international travel could be ready within the next 20 to 30 years. Companies are already working on spacecraft that could make such flights a reality. However, transitioning these technologies from space tourism to a viable transportation option for the general public will require careful development and regulatory frameworks. In summary, while some futuristic technologies may emerge in the next few decades, others, like teleportation and warp drives, are still centuries away. The timeline for development depends not just on technological progress, but also on global collaboration, investment, and overcoming significant scientific challenges. Teleportation offers an obvious advantage over other methods of travel. It's instantaneous. Unlike hypersonic planes or warp drives, which still require time to cover distances, teleportation would theoretically allow someone to move from one place to another in the blink of an eye, regardless of the distance involved. Another major advantage is that teleportation could eliminate the need for vehicles, infrastructure, and fuel. No more airplanes, rockets, or highways, just direct transportation from point A to point B. This could have huge environmental benefits, potentially reducing pollution and resource consumption. However, teleportation comes with significant disadvantages, primarily around safety and accuracy. The process of breaking down and reconstructing a person at the atomic level is fraught with risk. Any error in reassembling the body could result in catastrophic consequences, from physical deformities to death. Another disadvantage is the immense energy required for teleportation. While warp drives and hypersonic travel also demand vast amounts of energy, teleportation's energy needs are far greater due to the complexity of disassembling and transmitting quantum data. This energy demand might make teleportation impractical for widespread use. Privacy and security concerns also loom large with teleportation. If the technology falls into the wrong hands, it could be used for unauthorized access, surveillance, or even criminal activity. Ensuring secure, regulated use would be a major challenge, especially in a world where teleportation could bypass borders and physical barriers. On the other hand, teleportation could revolutionize global travel. Traditional methods like planes and trains are limited by geography, weather, and logistics, but teleportation would remove these barriers. It could open up new possibilities for business, leisure, and global connectivity that other technologies simply cannot match. Unlike hypersonic or space travel, teleportation could, in theory, allow for instantaneous transportation to other planets or even distant galaxies, provided the necessary quantum connections are established. This is something even the fastest warp drives could not achieve in real time. There's also the issue of personal experience. Traditional travel methods like flying or taking a road trip offer time for reflection, relaxation, or sightseeing. Teleportation would erase the journey altogether, making the process of travel a purely functional event. This might diminish the cultural and personal value associated with travel. Warp drives and space elevators maintain physical integrity during transport, offering a sense of continuity and safety. Teleportation, on the other hand, raises profound questions about identity and consciousness. If the original body is destroyed and recreated, is the person who arrives the same as the one who left? For global infrastructure, teleportation would eliminate the need for airports, train stations, and other traditional travel hubs. While this could be an advantage in terms of efficiency, it might also lead to economic disruption in industries built around these infrastructures. Entire sectors could become obsolete. Another disadvantage is the potential for teleportation to create social inequality. If the technology remains expensive or difficult to access, only the wealthy or privileged might benefit from it, deepening divides between those who can teleport and those who are stuck with slower, traditional methods of travel. In summary, teleportation presents incredible advantages in speed and efficiency, but faces significant challenges in terms of safety, energy use, and ethical concerns. While it could surpass other travel methods in many ways, the complexities involved mean it's far from being a clear-cut solution. Advances in AI and computing power are critical to making teleportation a reality. One of the biggest challenges of teleportation is processing the immense amount of data required to break down and reconstruct a human being at the atomic level. This is where AI could play a transformative role, helping to manage and analyze this complex information far more efficiently than current technology allows. AI algorithms could be used to simulate and optimize the teleportation process, ensuring that all the quantum states are properly captured and transmitted without errors. With machine learning, these systems could become more accurate over time, potentially reducing the risks involved in teleporting living beings. Quantum computing also has a major part to play in teleportation. Classical computers would struggle to handle the sheer data load required for teleportation, but quantum computers could process vast amounts of information simultaneously. Quantum algorithms could enable us to simulate molecular structures or solve complex problems involved in teleporting matter. AI could assist in maintaining quantum entanglement, which is essential for quantum teleportation. Through constant monitoring and real-time adjustments, AI systems might be able to keep particles entangled over longer distances, ensuring that the teleportation process remains stable throughout the transfer. One of the greatest hurdles for teleportation is error correction. AI could help develop advanced error correction systems that detect and fix issues during teleportation in real time. This would ensure that the transmitted information remains intact, reducing the chances of harmful glitches during reassembly. AI might also be crucial in developing teleportation infrastructure. Designing and constructing quantum networks for teleportation would require highly sophisticated planning, simulations, and optimization, tasks that AI systems excel at. These networks could span entire cities or even planets, connecting teleportation hubs and managing the flow of data. In terms of energy management, AI could optimize how power is used during teleportation, finding ways to make the process more efficient. By analyzing energy consumption patterns and predicting future needs, AI could help reduce the enormous energy requirements currently associated with teleportation technologies. As teleportation systems become more complex, AI could assist in automating much of the process. From ensuring particles are correctly entangled to coordinating the timing of quantum measurements, AI could handle many of the intricate tasks required, freeing human operators from having to manually control every aspect. AI's role in quantum cryptography would also help secure teleportation networks, making sure that data transferred through teleportation is encrypted and protected from tampering. As teleportation becomes more widespread, ensuring that private or sensitive information isn't intercepted will be essential. The increased computing power offered by AI-driven quantum computers could lead to breakthroughs in material science, potentially allowing scientists to develop the super-strong materials needed for teleportation devices. AI could simulate new compounds and test them in virtual environments, speeding up the development of critical teleportation technologies. AI could also assist in the ethical and philosophical considerations of teleportation by running simulations to predict the effects of teleportation on human consciousness and biology. These simulations could help us understand the long-term impact of teleporting living beings, guiding future developments in a responsible manner. Overall, advances in AI and computing power are not just helpful, but essential for the future of teleportation. Without these tools, we wouldn't have the processing capability, error correction, or optimization needed to make teleportation a feasible and reliable technology. Breakthroughs in quantum computing are paving the way for major advancements in teleportation technology. Traditional computers work with bits, representing data as ones and zeros, but quantum computers use qubits, which can exist in multiple states simultaneously. This allows quantum computers to process vast amounts of information at once, a crucial factor in making teleportation feasible. One of the most important breakthroughs came with the achievement of quantum supremacy. In 2019, Google's quantum computer, Sycamore, performed a calculation in minutes that would have taken a classical computer thousands of years. This milestone demonstrated the sheer potential of quantum computing to tackle previously unsolvable problems. Quantum teleportation requires managing incredibly complex quantum states, and quantum computers are uniquely equipped to handle this challenge. With their ability to process many variables at once, they can track the vast number of particles involved in teleportation and ensure that their quantum states are correctly transferred. Advances in quantum error correction are essential for teleportation. Quantum systems are prone to errors due to their sensitivity to environmental factors, but breakthroughs in error correction algorithms are helping quantum computers become more stable. This stability is crucial for ensuring that quantum information is accurately transmitted during teleportation. Another key development is the ability to entangle qubits across greater distances. Quantum entanglement is the foundation of quantum teleportation, and recent breakthroughs have allowed researchers to entangle qubits over much larger scales than previously possible. This opens the door to long-distance teleportation, potentially connecting distant locations. Quantum gates, which are used to manipulate qubits, have also seen significant improvements. These gates are essential for performing the operations needed to teleport quantum information. As researchers refine the efficiency and accuracy of quantum gates, they bring us closer to practical applications of teleportation. The development of quantum networks is another breakthrough with far-reaching implications. Quantum computers connected through quantum networks could share entangled particles, allowing for seamless teleportation of quantum states between machines. This could revolutionize communication, computing, and even how teleportation is conducted in the future. Superconducting qubits, one of the leading technologies in quantum computing, have seen major advancements. These qubits are capable of maintaining quantum states for longer periods, reducing decoherence and improving the overall performance of quantum systems. This longevity is key to sustaining quantum teleportation processes over extended durations. Photon-based qubits have also made strides. Photons, or particles of light, can travel long distances without losing coherence, making them ideal for transmitting quantum information. Recent breakthroughs in controlling and manipulating photon qubits could help build the quantum infrastructure needed for teleportation. Quantum computing has made progress in simulating complex systems. Teleportation requires the precise simulation of atomic structures, and quantum computers are capable of modeling these systems in ways that classical computers cannot. These simulations provide insights that are crucial for understanding how to teleport matter safely. As quantum computing continues to improve, it is also becoming more accessible. Companies like IBM and Google are making quantum computers available through cloud platforms, allowing more researchers to experiment with quantum teleportation and related technologies. This democratization of quantum computing accelerates the pace of discovery. The rapid pace of breakthroughs in quantum computing suggests that we are inching closer to the day when teleportation becomes more than just a theoretical possibility. These advancements are laying the foundation for a future where teleportation could be used in ways we're only beginning to imagine. Nanotechnology could play a pivotal role in the future of teleportation, especially when it comes to the precision required to break down and reassemble matter. Nanobots, tiny machines capable of manipulating matter at the atomic or molecular level, could be essential in managing the intricate process of teleporting complex structures like human bodies. At the nanoscale, materials behave differently, offering unique opportunities for control and manipulation. By using nanotechnology, scientists might be able to deconstruct a person atom by atom, ensuring that every particle is accurately mapped and prepared for transmission. This kind of precision is far beyond what we can achieve with current technology. Nanotechnology could also help address the challenge of reassembly. After teleportation, reconstructing matter exactly as it was is one of the biggest hurdles. Nanobots could be programmed to place atoms in their exact original positions, ensuring that the teleported object or person functions as intended, without any errors or missing pieces. Additionally, nanotechnology offers solutions for error correction during the teleportation process. If small mistakes occur during reassembly, nanobots could detect and correct these errors in real time, repairing any damage before it becomes problematic. This self-correcting ability would be essential for safe and reliable teleportation. Nanobots could also play a key role in quantum entanglement, which is necessary for quantum teleportation. By manipulating particles at the atomic level, they could help maintain the entanglement of qubits over long distances, ensuring a stable and secure teleportation process. In terms of energy efficiency, nanotechnology could contribute to reducing the vast amounts of energy required for teleportation. By optimizing the processes of deconstruction and reassembly, nanobots could help minimize energy waste and improve the overall sustainability of the technology. The medical applications of nanotechnology and teleportation are particularly promising. Nanobots could ensure that biological systems, such as organs, cells, and even DNA, are handled with the utmost care during teleportation, reducing the risk of biological errors or damage. Nanotechnology might also help manage the body's dynamic biological processes during teleportation. For example, nanobots could monitor and preserve the electrical signals in the brain or maintain the integrity of biological functions like heartbeat and respiration, ensuring that the teleported individual remains healthy and conscious throughout the process. The use of nanomaterials could also help create stronger, more efficient teleportation devices. Materials like graphene and carbon nanotubes, which have extraordinary strength and conductivity at the nanoscale, could be used to build more advanced teleportation machines that can withstand the immense demands of the technology. Nanotechnology might also assist in the transmission of quantum information. By developing nanoscale systems capable of encoding and transmitting quantum states with high accuracy, scientists could improve the fidelity of quantum teleportation, making it more reliable for practical use. Nanobots could also help in protecting the teleportation process from external interference. Since quantum states are highly sensitive to environmental factors, nanotechnology could be employed to shield the teleportation system from noise and disruptions, ensuring a clean and stable transfer of information. As nanotechnology continues to evolve, it could become one of the key enablers of teleportation. By providing the tools to manipulate matter at the smallest scales, nanotechnology offers solutions to some of the biggest challenges we face in turning teleportation from theory into reality. Biotechnological advancements are another critical factor in making teleportation possible, especially when it comes to transferring living matter. Teleporting a human being is vastly more complex than transferring inanimate objects due to the intricacies of biological systems. Biotechnology could offer the tools needed to address these challenges. One of the most significant contributions of biotechnology would be understanding and preserving the structure of DNA during teleportation. DNA holds the blueprint of life, and ensuring that every strand is accurately transmitted and reassembled is essential to maintaining the integrity of a living organism after teleportation. Biotechnology could also aid in managing cellular processes during teleportation. Cells are not static. They are constantly performing functions such as energy production, waste management, and protein synthesis. Advanced biotechnological tools could monitor these processes, ensuring that cells remain viable throughout the teleportation process. Another area where biotechnology could help is in preserving tissue structures. Teleporting tissues like muscles, organs, and skin requires maintaining their physical structure and functionality. Biotech solutions could ensure that complex tissues are reconstructed accurately, down to the arrangement of individual cells. Biotechnology might also play a role in managing the immune response during teleportation. Disrupting the body's normal functions, even temporarily, could trigger immune reactions. Advanced biotech tools could regulate immune activity to prevent harmful reactions during the breakdown and reassembly of the body. In terms of brain activity, biotechnology could be crucial for ensuring that neural connections and brain functions are maintained. The brain's complex network of neurons and synapses governs consciousness, memory, and behavior. Biotechnological advancements could help preserve these connections during teleportation, ensuring that the teleported individual retains their sense of self. The potential for biotech to develop artificial tissues and organs may also have a role in teleportation. If natural tissues don't survive the teleportation process, biotechnological advancements in regenerative medicine could offer solutions, helping to regenerate or repair damaged tissues upon arrival. Another biotechnological advancement is the development of bioinformatics, which could be key in storing and transmitting biological data. The sheer volume of data required to capture the molecular structure of a living organism is staggering, and bioinformatics could provide the systems necessary to handle this data efficiently. Biotech could also assist in the study and manipulation of quantum biology, which explores how quantum mechanics might influence biological processes. By understanding the quantum behaviors of biological systems, researchers could develop more refined teleportation methods that account for the unique properties of living matter. In the area of synthetic biology, researchers are working on building custom organisms and biological systems from scratch. This field could intersect with teleportation by offering insights into how biological matter can be deconstructed and reconstructed, potentially creating new ways to transfer living organisms. Biotechnology also offers hope in managing the ethical implications of teleporting living beings. By understanding the biological processes involved at a deep level, we can make more informed decisions about how to approach the risks and benefits of teleporting humans, ensuring that these processes are as safe and ethical as possible. In the future, the convergence of biotechnology and teleportation could lead to a new era of human travel. By applying biotech solutions to the challenges of matter transfer, we move one step closer to making teleportation a viable method of transporting living matter safely and effectively. Theoretical research on energy manipulation is crucial for understanding how teleportation could one day become possible. At its core, teleportation requires the ability to break down matter into its fundamental components and then reassemble it, a process that would demand unprecedented control over energy. One of the primary focuses of this research is on manipulating quantum energy states. Quantum particles, such as photons or electrons, can exist in multiple states at once, and controlling these energy states is essential for quantum teleportation. By harnessing the energy properties of these particles, scientists hope to develop methods for more efficient matter transfer. Another key area of research is zero-point energy, a concept from quantum mechanics. Zero-point energy is the lowest possible energy that a quantum system can have, even in a vacuum. Theoretically, tapping into zero-point energy could provide a nearly limitless power source for teleportation, though this remains speculative. The relationship between mass and energy, as described by Einstein's famous equation E=mc2, is also central to the idea of teleportation. Converting mass into energy and back again requires extraordinary amounts of power. Theoretical research is exploring ways to make this conversion more efficient, reducing the energy demands of teleporting physical objects. Scientists are also investigating the potential of manipulating dark energy, the mysterious force driving the expansion of the universe. If we could tap into or control dark energy, it might offer a new way to overcome the energy barriers associated with teleportation, though this remains highly theoretical. Plasma physics is another field contributing to energy manipulation research. Plasma, the fourth state of matter, contains highly charged particles that could potentially be used to create the conditions needed for teleportation. The ability to manipulate plasma at will might provide the energy dynamics necessary for teleporting matter. There is also research into the use of antimatter, which releases massive amounts of energy when it comes into contact with regular matter. Although antimatter is extremely difficult to produce and store, its energy potential could be key to overcoming the enormous power requirements of teleportation. Theoretical work on energy fields is another area of interest. Scientists are exploring whether controlled energy fields could act as a framework for transporting matter, holding particles in place as they are transferred from one location to another. Such energy fields could help stabilize the teleportation process. The study of energy conversion is equally important. Research into converting different types of energy, such as electromagnetic or thermal energy, into the forms needed for teleportation, is advancing. Efficient energy conversion methods would be critical in reducing the overall power needed for teleportation technology to function. One of the more speculative areas involves the concept of manipulating gravitational energy. Some theories suggest that if we could control gravity, it could open up entirely new possibilities for how energy is used in teleportation, potentially reducing the reliance on other energy forms. Another promising area is the use of quantum vacuum energy, the energy present in empty space. Theoretical physicists are examining whether this energy could be harnessed to power teleportation processes, as it exists everywhere in the universe, and could provide a consistent source of power. Ultimately, the theoretical research into energy manipulation is still in its infancy, but it holds the key to solving one of the most significant challenges of teleportation: the vast amount of energy required. As our understanding of energy continues to evolve, we may unlock new ways to control and use it, bringing teleportation one step closer to reality. The question of identity and the continuity of self is one of the most profound issues surrounding teleportation. If a person is disassembled at the molecular level and then reassembled elsewhere, are they still the same person? Or is the original consciousness lost in the process, replaced by a perfect copy? This dilemma touches on deep philosophical debates about the nature of identity. What makes someone who they are? Is it their physical body, their memories, or something more abstract like their consciousness? Teleportation challenges these ideas by disrupting the continuity of the body during transport. One concern is whether the teleportation process would result in the destruction of the original individual. If the original body is completely broken down, does that mean the person is effectively killed during teleportation, with a new version of them emerging on the other side? This raises the issue of whether the mind can survive such a process. The brain is responsible for our thoughts, emotions, and memories. But if it is dismantled and reassembled, is the consciousness that returns truly the same? Or has the original mind ceased to exist, replaced by a duplicate that only believes it's the same person? Some theorists argue that as long as the reassembled body is identical and the memories are intact, the person remains the same. Others contend that even a perfect copy would lack the continuity of the original, making the teleported individual a new entity, not the one who started the journey. The concept of personal identity over time is also challenged. If every particle in a person's body is replaced during teleportation, can we still consider them the same individual? Or has the teleportation process fundamentally altered their identity, even if they appear unchanged? Continuity of self is often tied to the unbroken flow of consciousness, but teleportation, which involves the complete disintegration of the body, disrupts this flow. Even if reassembled perfectly, the question remains, did the consciousness experience an interruption, or does it continue seamlessly through the process? There's also the question of whether teleportation creates multiple versions of a person. If, for some reason, the original isn't fully destroyed, you could theoretically have two identical individuals with the same memories and personality. This raises ethical concerns about the duplication of identity. The philosophical concept of the ship of Theseus is often used as a metaphor for teleportation. If every part of a ship is replaced, is it still the same ship? In teleportation, if every atom of a person is replaced during reassembly, are they still the same person, or just a new version of the original? Even if teleportation could perfectly replicate the body, it may not be able to replicate the subjective experience of being that person. There's a mystery surrounding consciousness, something we don't fully understand, which makes it difficult to determine whether teleportation preserves or disrupts the essence of self. In practical terms, these questions could have legal and ethical implications. Would a teleported person retain their legal identity and rights, or would they be considered a new individual? How would society address the philosophical and legal ramifications of potential identity discontinuities? Ultimately, teleportation forces us to confront the most fundamental aspects of what it means to be human. Until we fully understand the nature of consciousness and identity, the idea of teleporting people will remain deeply controversial, raising more questions than it answers. The moral considerations of duplication and destruction in teleportation are some of the most troubling aspects of the technology. If teleportation involves creating a perfect copy while destroying the original, is it ethically acceptable to proceed with such a process? The destruction of the original body, even in the service of transport, raises questions about the sanctity of life. Some argue that if the reassembled person is an exact duplicate, there's no real harm done. After all, the copy would think, feel, and act exactly as the original, with the same memories and personality. But others contend that the destruction of the original body constitutes a form of death, even if the copy continues as if nothing had changed. This brings up the issue of consent. Would people truly consent to teleportation if they understood that the process might involve their original body being destroyed? Informed consent becomes critical here, especially if individuals don't fully grasp the implications of what's happening to them. If teleportation allows for duplication without destruction, the ethical concerns grow even more complex. Multiple versions of a person could exist simultaneously, leading to questions about identity, responsibility, and the nature of individuality. Would these duplicates share the same rights and responsibilities as the original? From a moral standpoint, the possibility of duplicating a person could lead to exploitation. What if people were cloned without their knowledge or consent? The potential for abuse is significant, and any teleportation technology capable of duplication would require strict ethical guidelines and regulations. There's also the question of whether the destruction of the original body is necessary at all. If teleportation could work without destroying the original, would society then face the dilemma of managing multiple versions of individuals? The existence of multiple copies raises serious concerns about personal accountability and identity. Another moral concern is the value we place on continuity of consciousness. If teleportation destroys the original body and creates a copy, does this sever the continuous thread of existence? Some argue that breaking this continuity, even temporarily, amounts to a violation of the individual's personal identity. There are potential scenarios where teleportation might fail to destroy the original body, leaving behind two identical individuals. In such cases, moral dilemmas would arise around which version of the person has the right to continue their life, relationships, and responsibilities. Who would be considered the true individual? The destruction involved in teleportation could also lead to unintended harm. If something goes wrong during the process, both the original and the copy could suffer. Ensuring that the technology is safe and reliable is a moral imperative before it can be widely used. The idea of teleportation as a form of assisted suicide is another disturbing consideration. If the original is destroyed each time, does the process effectively end one life while allowing a copy to continue? This challenges fundamental beliefs about life, death, and the value of human existence. Legal systems would also struggle to address the implications of duplication and destruction. How would laws around identity, inheritance, and personal rights adapt to a world where multiple versions of the same person could exist, or where the original person is regularly destroyed in the process of teleportation? Ultimately, the moral considerations surrounding duplication and destruction in teleportation force us to rethink long-held assumptions about the value of life, identity, and individuality. Without clear ethical frameworks in place, the technology risks creating more problems than it solves. Teleportation also raises significant privacy concerns that go beyond traditional methods of travel. With teleportation, the process involves breaking down a person or object into detailed, potentially sensitive data. This data, if not properly secured, could be vulnerable to interception, hacking, or misuse. Every part of your physical body, including your DNA and biological information, would be digitized for teleportation. This means that highly personal information about your physical being could be stored or transmitted across networks, creating risks of unauthorized access. Who controls and protects this data? In an age where data privacy is already a hot-button issue, teleportation adds a new dimension to the debate. If your entire physical structure can be reduced to data, what happens if that data falls into the wrong hands? This could lead to theft of identity, cloning, or other forms of exploitation. Teleportation could also make it easier for governments or corporations to track individuals. If teleportation is widely adopted, each trip could be logged, monitored, and stored in databases, creating a detailed record of everyone's movements. The potential for surveillance would increase dramatically, raising serious concerns about personal freedom. The centralization of teleportation systems could place immense power in the hands of those who control the technology. With the ability to track, monitor, and even deny access to teleportation, organizations could control not just where people go, but also how and when they travel. This level of control could lead to significant abuses of power. There's also the issue of consent. Would people be fully aware of how their teleportation data is being used or stored? Without transparency, individuals may unknowingly give away access to their most personal information with no way to reclaim it or control how it's used in the future. Another privacy concern is the potential for teleportation to be used for illegal or unethical surveillance. In theory, someone could teleport into a restricted or private area without leaving a trace, bypassing traditional security measures. This would create new challenges for maintaining security and enforcing privacy laws. Beyond individual privacy, there's the question of intellectual property. If objects or even living beings can be teleported, What safeguards would be in place to prevent unauthorized duplication or theft? Protecting the integrity of both people and physical items would become a critical issue in a world where teleportation exists. Teleportation could also impact digital privacy in unexpected ways. If the technology involves transmitting data through networks, that data could be susceptible to the same risks as other digital information. Data breaches, cyber attacks, and even manipulation of teleportation data could lead to dangerous consequences. In a scenario where teleportation becomes commonplace, data security protocols would need to evolve dramatically. Encryption, authentication, and strict privacy regulations would be essential to protect the sensitive information involved in teleportation. However, these measures may still struggle to keep up with the rapidly advancing technology. There's also the risk of data being stored long after a person has teleported. If detailed information about your physical self remains archived, what happens if it's accessed later, without your consent? The concept of permanent digital records of a person's physical being adds a layer of complexity to privacy concerns. Ultimately, teleportation introduces unprecedented privacy risks that must be addressed before the technology can be safely implemented. Without stringent privacy protections, teleportation could lead to the erosion of personal freedoms, making it even more crucial to balance innovation with the preservation of privacy rights. The societal impacts of instant travel through teleportation would be profound, reshaping how we live, work, and interact with each other. With the ability to travel instantly anywhere in the world, traditional concepts of distance and geography would become almost irrelevant, transforming industries and economies globally. One of the most immediate changes would be in the workplace. People could live anywhere and still instantly appear at their jobs. The need for offices or centralized workplaces might disappear, leading to new forms of remote work that are even more flexible than current models. This could also shift real estate markets, as people would no longer need to live close to their place of work. Tourism would likely see a massive boom. With the ability to teleport anywhere in the world, more people would be inclined to visit far-off destinations without worrying about travel time or costs associated with flights. Popular tourist destinations could see a surge in visitors, while more remote locations might become accessible to the masses. However, this influx of tourism could also lead to overcrowding in certain areas. The ability to instantly travel could overwhelm infrastructure, leading to issues with sustainability, preservation of natural environments, and the management of public spaces. Local economies may struggle to balance the benefits of increased tourism with the strain on resources. Teleportation could also change how we think about borders and national sovereignty. With the ability to move instantly across countries, regulating immigration and enforcing borders would become much more difficult. Governments might need to develop entirely new systems for controlling movement and ensuring security. Culturally, teleportation could break down barriers between nations. Instant access to different cultures could lead to more cultural exchange, potentially fostering greater understanding and cooperation. At the same time, it could also challenge traditional cultural identities, as the lines between regions blur. In education, students could attend classes anywhere in the world instantly. Access to top-tier schools and universities would no longer be limited by geography. This could lead to a more democratized education system, where people from all corners of the globe can learn together and share knowledge in real time. On the other hand, the convenience of teleportation might reduce the value we place on travel and exploration. If visiting a new place becomes as easy as a single step, the sense of adventure and discovery might diminish. The journey itself, often considered a valuable part of the travel experience, would be lost. Teleportation could also change how communities function. People might be less inclined to form strong local ties if they can easily maintain relationships with friends and family across the globe. This could weaken community bonds, as the need for proximity in relationships is diminished. The environmental impact of teleportation could be significant as well. If it replaces traditional modes of transportation like airplanes, cars, and ships, it could drastically reduce carbon emissions. However, the energy demands of teleportation are likely to be immense, raising questions about sustainability. Society's approach to time management would also change. With no need to factor in travel time, people could pack more into their daily lives. While this could increase productivity, it might also lead to heightened stress and an expectation that people are always available, potentially eroding work-life balance. In the end, teleportation would likely have both positive and negative effects on society. While it offers incredible opportunities for convenience, connection, and growth, it also brings challenges that would require careful management to ensure that the benefits outweigh the potential drawbacks. The potential for teleportation to be misused in warfare and crime is a serious concern. In warfare, teleportation could offer a strategic advantage, allowing armies to deploy troops, weapons, or supplies instantly to any location. This could destabilize traditional defense systems and make it difficult to predict or prevent attacks. Teleportation could also be used to bypass borders and infiltrate secure areas. Military forces could use it to strike deep within enemy territory without warning, making it nearly impossible to protect key infrastructure or government facilities. This would force nations to completely rethink their defense strategies. In the hands of criminals, teleportation could make illegal activities far more difficult to control. Smugglers could transport drugs, weapons, or other contraband across borders without detection. Law enforcement agencies, already challenged by international crime, would face even greater difficulty tracking and stopping these operations. Teleportation could be used to evade capture as well. Criminals could disappear from the scene of a crime in an instant, leaving no trace behind and making it nearly impossible for authorities to pursue them. This could result in a dramatic increase in unsolved crimes and a loss of trust in the justice system. There's also the risk of teleportation being used for personal gain in unethical ways. Thieves could teleport into secure locations such as banks or vaults, stealing valuables without triggering alarms or security systems. The very idea of physical security would need to be redefined in a world where teleportation exists. Terrorism could take on a new dimension with teleportation. Attackers could target crowded public spaces or critical infrastructure, delivering explosives or other weapons instantly. This would make it incredibly difficult to detect or prevent attacks, heightening the threat level and increasing fear within society. Kidnapping and human trafficking could become more sophisticated as well. Teleportation would allow criminals to abduct individuals and transport them across great distances in moments, making it harder for authorities to locate victims or track their movements. The black market for teleportation technology could also flourish. If access to teleportation devices were restricted, criminals would likely seek ways to acquire or build their own, leading to an underground trade in this technology. The consequences of teleportation falling into the wrong hands could be catastrophic. Another risk involves espionage. Teleportation could allow spies to infiltrate foreign governments or corporations, collecting sensitive information without being detected. The ability to gather intelligence instantly and return undetected would give an unprecedented advantage to those involved in espionage. Privacy violations would also be a major concern. Stalkers or those with malicious intent could use teleportation to invade people's private spaces, bypassing locks, alarms, or other security measures. The sense of personal safety could be severely compromised if teleportation technology isn't strictly regulated. Sabotage would become more dangerous as well. With the ability to teleport into secure locations, individuals could tamper with critical infrastructure, such as power plants or communication networks, without being caught. This could lead to widespread chaos and significant damage to public systems. Ultimately, the potential for misuse in warfare and crime highlights the need for strict controls and regulations on teleportation technology. Without careful oversight, the dangers posed by this new form of travel could outweigh its benefits, leading to an increase in global instability and personal risk. Teleportation, as portrayed in movies and TV, often leads to misconceptions about how the process would actually work. In many fictional stories, teleportation appears instantaneous and effortless, with no mention of the complex science or technology that would be required. This can make the concept seem much simpler than it truly is. One common misconception is that teleportation involves a person simply disappearing and reappearing somewhere else. In reality, teleportation, as we understand it scientifically, would require breaking down an individual into data, transmitting that data, and then reconstructing the person at the destination. This process is far more complicated than just vanishing and reappearing. Fictional portrayals rarely address the massive energy requirements for teleportation. In shows and films, characters are teleported without any mention of the enormous amounts of power that would be needed to disassemble and reassemble a person. The real-world energy demands would likely be one of the biggest barriers to achieving teleportation. Another misconception is that teleportation would be completely safe and error-free. In many stories, there's little concern about what could go wrong during the process. However, in reality, even the smallest error in reassembling atoms could result in catastrophic consequences, potentially leaving the individual severely injured or worse. The idea that teleportation is instant also overlooks the need for time to process and transmit the massive amounts of data required to transport a human body. Even with advanced technology, transmitting that data might still take time, making truly instantaneous teleportation difficult to achieve. Movies and TV also tend to gloss over the philosophical and ethical implications of teleportation. Characters often teleport without ever questioning whether the person who arrives is the same person who left. In reality, the destruction and duplication of a person would raise profound questions about identity and continuity of consciousness. Teleportation in fiction is often portrayed as a form of magical or futuristic technology that works without explanation. In reality, quantum teleportation, the most promising scientific approach, only transfers information about quantum states, not actual matter. This is very different from the physical teleportation seen in popular media. Fictional teleportation devices are often depicted as small, portable, and easy to use. In truth, any teleportation technology that could disassemble and reassemble a human would require incredibly sophisticated and likely massive machinery. The idea that a small handheld device could accomplish this is far from realistic. Another misconception is that teleportation would be available to everyone equally. In many stories, it's portrayed as a universal technology. However, the cost, infrastructure, and energy demands of teleportation would likely make it a highly restricted technology, at least in the beginning, accessible only to a select few. Movies and TV often ignore the biological complexities of teleporting a living organism. The idea of perfectly reconstructing cells, tissues, and organs is taken for granted, but in reality, ensuring that biological systems function correctly after teleportation would be one of the greatest challenges. Fiction also tends to assume that teleportation could be done over any distance without issues. In reality, quantum teleportation experiments have only succeeded over relatively short distances, and scaling this up to cover vast distances, such as between planets, presents enormous challenges. The risk of teleportation being used for unethical purposes, such as espionage or crime, is also rarely explored in depth in fiction. While some stories touch on these ideas, the true extent of the dangers associated with teleportation, particularly the risk of misuse, are often downplayed for the sake of narrative simplicity. Overall, while teleportation in movies and TV captures our imagination, it's important to recognize that the real-world challenges and implications are far more complex. The technology, if ever achieved, would likely be very different from the effortless, instantaneous process we've seen on screen. The real science behind teleportation is vastly different from what we often see in fiction. While movies and TV depict teleportation as a quick and effortless process, actual scientific research is focused on teleporting quantum information, not physical matter. Quantum teleportation involves transferring the state of particles, not moving objects or people. In fiction, teleportation usually means instantly traveling from one place to another. In reality, quantum teleportation relies on the principle of quantum entanglement, where two particles remain connected regardless of distance. This allows for the transfer of information between them, but it doesn't involve physically moving the particles themselves. One major difference between real science and fiction is the complexity involved. Fictional teleportation devices are often portrayed as simple and user-friendly, but real-world teleportation would require incredibly advanced technology, capable of handling immense amounts of data and energy. In the scientific realm, teleportation is limited to very small particles like photons. We are nowhere near the ability to teleport complex objects or living beings. Fiction often skips over these technical limitations, offering a far more optimistic view of teleportation technology. Fiction also tends to ignore the immense data processing required for teleportation. To teleport a person, we would need to scan and store every atom and every bit of information about their physical structure. This level of detail would require computing power far beyond what is available today. Another key difference is the time involved. In fiction, teleportation is often portrayed as instantaneous. But in reality, even if we could teleport a human, the process of scanning, transmitting, and reassembling that data could take time, especially over long distances. In movies and TV, the risks of teleportation are usually downplayed or non-existent. In the real world, teleporting a human would come with a host of risks, from data loss to reconstruction errors. The possibility of something going wrong would make teleportation a much riskier endeavor than it appears in fiction. In science, teleportation is an active area of research, but it's focused on information transfer, not the physical movement of objects. Quantum teleportation has been successfully demonstrated over short distances, but we are still far from being able to apply this to anything beyond small particles. Teleportation in fiction often avoids addressing the energy requirements. In reality, the energy needed to break down and reconstruct a human body, atom by atom, would be astronomical. The idea that teleportation could happen with the flick of a switch doesn't align with the significant energy challenges we face. While teleportation in fiction provides an exciting narrative, the scientific reality is that teleportation is still in its infancy. Scientists are making strides in quantum teleportation, but the leap to human or object teleportation is still far in the future. The complexity of biology, data, and quantum physics makes the challenge much greater than what is shown on screen. In fiction, the philosophical and ethical implications of teleportation are often overlooked. But in real science, these questions are critical. The destruction and recreation of a person raise deep questions about identity, continuity, and the nature of consciousness, issues that the science community continues to explore. Ultimately, while fiction makes teleportation seem like a convenient tool for travel, the real science tells a different story. We are only just beginning to understand the possibilities, and it will take many more decades, if not centuries, before teleportation becomes anything close to the seamless, instant travel we see in movies. Popular media has always played a significant role in shaping public perception of scientific research. Teleportation, often glamorized in movies and television, has inspired curiosity and excitement about the possibilities of future technology. This widespread interest has sometimes pushed scientists to explore concepts that were first imagined in fiction. In many ways, science fiction serves as a form of speculative research, presenting ideas that seem impossible, but encourage real-world scientists to think outside the box. The depiction of teleportation in popular media has motivated researchers to delve deeper into quantum mechanics and other advanced fields of physics, driven by the desire to turn fantasy into reality. However, the simplified and often exaggerated portrayals of teleportation can lead to unrealistic expectations. People who are fascinated by fictional teleportation may assume that science is closer to achieving it than it actually is. This can result in frustration or skepticism when they realize the technology is still in its infancy. On the flip side, the influence of media can lead to increased funding and support for research into concepts like teleportation. When the public becomes captivated by an idea, governments and private investors are more likely to fund projects that align with those interests, even if they seem far-fetched. Popular media also helps communicate complex scientific ideas in a more digestible way. By introducing concepts like quantum entanglement or particle physics through entertaining stories, media can spark curiosity in younger generations and inspire the next wave of scientists and innovators to explore these fields. At the same time, there's a risk that media representations oversimplify the science behind teleportation, glossing over the real challenges involved. This can create a disconnect between what is shown on screen and the actual progress being made in laboratories, leading to misunderstandings about the nature of scientific research. Media can also influence the ethical discussions around teleportation. By exploring the moral dilemmas of identity, consciousness, and privacy in fictional narratives, media brings these issues into the public eye, encouraging broader conversations about the implications of future technologies. In some cases, media portrayals have even influenced the direction of scientific research. Scientists sometimes take inspiration from fictional technologies, using them as a blueprint for their real-world experiments. The way teleportation has been envisioned in films like Star Trek or The Fly has sparked debates within the scientific community about how such technologies could function. Media attention on teleportation can also create hype, sometimes overshadowing more realistic advancements in science. While teleportation may be far off, other emerging technologies, like quantum computing or artificial intelligence, could have more immediate impacts, yet receive less attention because they lack the same cinematic appeal. Furthermore, the widespread fascination with teleportation in media has led to an increase in educational programs focused on quantum mechanics and theoretical physics. Universities and institutions often see a spike in interest in these subjects when popular shows or movies introduce their audiences to these complex topics. Media also has the power to shape the public's expectations of how teleportation should work. If the general population is conditioned to believe that teleportation will be as simple and risk-free as depicted in fiction, it may lead to disappointment or resistance when real-world science presents a more complicated and cautious approach. Ultimately, while popular media's impact on scientific research is mixed, it undeniably plays a role in shaping the future of science. By inspiring both scientists and the public to think creatively about teleportation, media continues to influence the course of research, pushing the boundaries of what we imagine to be possible. Entertainment has always played a crucial role in inspiring scientific exploration. From early science fiction novels to modern blockbuster films, stories about futuristic technologies often spark real-world curiosity and innovation. Teleportation is no exception, with its portrayal in media igniting interest in quantum physics and the possibilities of breaking the limits of space and time. The power of entertainment lies in its ability to present ideas in a way that captures the imagination. When audiences see teleportation on screen, they aren't just watching a fictional event. They are engaging with a concept that challenges their understanding of reality. This can lead to a desire to explore the science behind what seems fantastical. Many scientists have credited their interest in fields like physics or engineering to their exposure to science fiction as children. Films and TV shows that feature advanced technologies, like teleportation, often plant the seeds of inspiration in young minds, encouraging them to pursue careers in scientific research. Entertainment can also serve as a testing ground for new ideas. By presenting speculative concepts like teleportation, creators allow audiences, and by extension scientists, to explore the potential implications of these technologies. This kind of creative thinking helps push the boundaries of scientific inquiry, forcing researchers to ask, what if? There's a symbiotic relationship between entertainment and science. While science informs and shapes the world-building in films and television, these fictional worlds, in turn, inspire scientists to think about new ways to solve problems or push the limits of what's possible. Teleportation as imagined in media may be fiction today, but it could influence tomorrow's scientific breakthroughs. Moreover, entertainment often presents technological challenges that scientists may not have considered before. By seeing teleportation depicted in all its dramatic glory, researchers are inspired to address the scientific hurdles that make such technologies seem impossible. These challenges motivate further exploration and experimentation. Storytellers have a unique ability to frame complex scientific ideas in a way that's accessible to the general public. Through visual effects and creative storytelling, films and TV shows can demystify concepts like quantum entanglement, making them more relatable and encouraging more people to engage with scientific topics. Even though the teleportation in entertainment is fictional, it helps normalize the idea of extraordinary scientific progress. When audiences repeatedly see concepts like teleportation portrayed in popular culture, they become more open to the possibility that these technologies could one day be real. This shift in mindset is critical for fostering a society that embraces scientific advancement. Entertainment also creates a shared cultural vocabulary. When people think of teleportation, they often reference iconic moments from shows like Star Trek or films like Jumper. These references create a common understanding of the concept, making it easier for scientists, educators, and the general public to communicate and explore ideas together. However, while entertainment inspires, it can also lead to misconceptions about how easy or fast scientific progress happens. When teleportation is depicted as a simple push of a button, it can create unrealistic expectations, for when such technologies might be achievable. Scientists often have to manage these expectations, reminding people that real-world innovation takes time. Still, the inspiration drawn from entertainment cannot be understated. The dreams sparked by science fiction lead to real-world inventions, from space exploration technologies to medical advancements. Teleportation, as portrayed in films and TV, continues to be one of the most enduring symbols of humanity's desire to transcend physical limitations. In the end, the role of entertainment in inspiring science is clear. It serves as a catalyst for curiosity, creativity, and innovation, encouraging both scientists and the general public to dream of a future where the impossible becomes possible. Whether or not teleportation ever becomes a reality, its place in entertainment will continue to fuel the drive to explore the unknown. Teleportation, as portrayed in popular media, is often far removed from scientific reality. In most films and TV shows, it appears as an effortless process where characters are instantly transported from one location to another. This portrayal tends to oversimplify the immense technical and scientific challenges involved. One major difference is that fiction rarely addresses the complexity of disassembling and reassembling matter at the atomic level. In reality, this would require mapping every atom in a person's body and transmitting that information perfectly. The sheer amount of data involved is often overlooked in fictional depictions. Movies and TV shows also fail to mention the energy requirements for teleportation. In fiction, teleportation is often powered by devices that seem to require little energy, but in real life, the amount of energy needed to break down and reconstruct matter would be astronomical. Another unrealistic aspect is the idea of instantaneous teleportation. While teleportation in fiction is nearly always immediate, real-world teleportation, if it were possible, would likely take time. The process of scanning, transmitting, and reassembling all the necessary data would not happen in an instant. Fiction tends to ignore the risks of teleportation as well. Characters in movies and TV rarely suffer from errors or accidents during the process. In reality, even a minor error in reconstructing a person could have disastrous consequences. Yet this danger is rarely explored in entertainment. There's also little discussion in media about the philosophical implications of teleportation. The idea of destroying the original person and creating a perfect copy is often brushed aside, with no examination of whether the teleported individual is truly the same as the one who left. Teleportation devices in fiction are often depicted as small and easy to use, but in reality, any machine capable of teleporting a person would likely be large and incredibly complex. The technology required to achieve such a feat would involve highly sophisticated systems far beyond what is shown on screen. One of the biggest misconceptions from fiction is that teleportation is a universal technology, accessible to anyone. In reality, if teleportation were ever developed, it would likely be expensive and limited to specific uses, at least in the beginning. Fiction tends to overlook the economic and practical limitations. The portrayal of teleportation across vast distances, such as from one planet to another, is also unrealistic. Quantum teleportation experiments have only been successful over short distances, and scaling this up to planetary or interstellar distances remains an enormous challenge. In many shows and movies, teleportation is depicted as being seamless with no side effects. But in the real world, teleporting living beings would involve significant biological risks. Fiction rarely addresses how complex systems like the brain or nervous system would handle being disassembled and reassembled. Teleportation in fiction often assumes that it's a technology without any moral or ethical concerns. However, in reality, there would be serious questions about identity, privacy, and the potential for misuse. These issues are largely ignored in favor of a cleaner, more convenient narrative. Ultimately, while teleportation in media is entertaining and visually stunning, it doesn't reflect the real scientific, technological, and ethical challenges involved. The process, as we understand it today, is far more complex and fraught with issues than what is portrayed on screen. Teleportation would have dramatic economic impacts across multiple industries. One of the most immediate effects would be on transportation. Airlines, railways, shipping companies, and even rideshare services could face massive disruptions as teleportation makes traditional forms of travel obsolete. The global shipping industry, which relies on the transport of goods across oceans and continents, would be transformed. With teleportation, products could be moved instantly from factories to consumers, drastically reducing shipping times and costs. This could also disrupt supply chains, as companies would no longer need to maintain large inventories or deal with delays. Teleportation could revolutionize international trade by removing geographic barriers. Businesses could operate more efficiently, trading goods and services globally without the costs and logistical challenges of moving products through traditional transportation methods. This could lead to lower prices for consumers and increased competition in the market. However, the loss of jobs in traditional transport sectors could lead to economic instability. Millions of people who work in logistics, shipping, and transportation could face unemployment as teleportation technology takes over. Governments would need to create new policies to support workers and help them transition to other industries. Real estate markets would also feel the effects. With teleportation eliminating the need to live near workplaces, housing demand could shift. Urban centers might see a decrease in population as people move to more remote or desirable locations, leading to changes in property values and the way cities are structured. Retail and e-commerce would be impacted as well. Teleportation could lead to a new era of on-demand shopping, where consumers can order products and have them delivered instantly. This could create new business models and increase consumer spending, but would likely disrupt the traditional retail sector. The tourism industry could see a significant boom. With instant travel, people might be more inclined to visit distant locations that were previously time-consuming or expensive to reach. Popular tourist destinations might experience a surge in visitors, while more remote places could become accessible for the first time. Energy costs could also change dramatically. While teleportation would likely require vast amounts of energy, it could reduce the need for fossil fuels used in transportation. The economic effects of this shift could disrupt energy markets, with demand for oil and gas declining as teleportation becomes more widespread. Telecommunication companies might face new challenges as well. With instant travel, the need for long-distance communication could decrease, as people would be able to teleport to meetings or social gatherings in person. This could reduce demand for certain communication technologies, while creating new opportunities for companies that support teleportation infrastructure. At the same time, the high cost of teleportation technology could initially restrict its use to wealthy individuals and corporations, creating economic divides. Those with access to teleportation could have a significant advantage in business, travel, and access to resources, potentially deepening inequalities. Insurance industries might also have to adapt, with the potential risks associated with teleportation, such as accidents or data breaches during transport. New types of insurance policies would be needed. The development of teleportation-specific insurance could become a major new market. Overall, teleportation would create both opportunities and challenges for the global economy. While it could bring increased efficiency, lower costs, and new business models, it would also disrupt entire industries, create new social divides, and require significant adjustments to existing economic systems. Teleportation would have a profound effect on international relations and politics, fundamentally altering how countries interact with one another. The ability to instantly travel across borders could make it harder for nations to enforce immigration laws and control their territorial boundaries, leading to tensions between governments. Diplomacy could be transformed as leaders, and diplomats could attend international summits and meetings instantly, no longer limited by travel time or logistical constraints. This could speed up negotiations but also increase the pressure for rapid decision-making in crises, leaving less time for careful deliberation. Teleportation could also disrupt global security. If militaries gain access to teleportation technology, it could lead to an arms race, with nations striving to gain a strategic advantage. The ability to move troops or weapons instantly across the globe would challenge existing defense systems and potentially destabilize global peace. Nations with advanced teleportation capabilities could hold significant power over those without. Countries with limited access to the technology might be at a disadvantage in trade, military strength, and international influence, deepening global inequality and shifting the balance of power. Border security would become more difficult to manage. Teleportation could enable individuals to cross borders without detection, complicating efforts to control illegal immigration, smuggling, or the movement of contraband. Governments might need to invest in entirely new security infrastructures to monitor and regulate teleportation. Global cooperation could be both helped and hindered by teleportation. On one hand, the ability to travel instantly could promote more frequent collaboration between nations on issues like climate change, health, and education. On the other hand, disputes over the regulation, control, and use of teleportation technology could fuel geopolitical tensions. International trade agreements would need to be rewritten. Teleportation could eliminate traditional shipping routes and trade barriers, forcing countries to rethink tariffs, customs, and trade policies. New frameworks would be needed to account for goods and services moving instantly across borders. The United Nations and other international organizations might face pressure to establish global regulations for teleportation. Without coordinated oversight, the technology could be used unethically or unfairly, with some nations exploiting it to their advantage. International treaties governing its use might become necessary. National sovereignty could be challenged. The ability to teleport anywhere could make it harder for governments to control their own citizens or keep foreign influence at bay. Countries could see an increase in foreign interference, espionage, or even cyber attacks facilitated through teleportation. Economic competition between countries would intensify. Nations that embrace teleportation early could gain a significant economic edge, attracting businesses, investment, and talent. Meanwhile, countries slow to adopt the technology might struggle to keep up, further widening the gap between developed and developing nations. Public opinion and political discourse could be shaped by teleportation's impact. Governments that fail to manage its effects on jobs, security, or privacy could face backlash from their populations. Politicians might use teleportation as a campaign issue, promising reforms or protections related to the technology's use. Ultimately, teleportation would force a rethinking of many aspects of international relations and politics. While it could bring countries closer together through instant communication and collaboration, it also has the potential to create new divides and challenges that could reshape the global order. Teleportation would cause a massive disruption to the travel industry. Airlines, cruise lines, and rail companies could become obsolete almost overnight, as people opt for the convenience of instant travel over traditional methods. The demand for these services would plummet, leading to widespread job losses and industry collapse. Hotels and hospitality could also face major challenges. If people can teleport instantly to any destination, there may be less need for accommodations. Travelers could visit a location for a few hours and return home the same day, reducing the need for long-term stays in hotels, motels, or vacation rentals. The shipping industry would undergo a complete transformation. Goods that currently take days or weeks to transport across oceans could be delivered instantly, making traditional cargo ships and freight transportation irrelevant. This would not only affect shipping companies but also impact ports, warehouses, and logistics firms. E-commerce could see radical changes as well. With instant teleportation of goods, customers could receive products the moment they order them, completely reshaping the expectations for delivery times. Companies that rely on speedy shipping as a competitive advantage would need to adapt quickly to keep up. The automotive industry might suffer as well. With the ability to teleport, the need for personal vehicles could decline, as people may no longer require cars for commuting or long-distance travel. Car manufacturers, fuel companies, and auto repair industries could all face significant challenges as demand shrinks. Public transportation networks, from buses to subways, could also become less relevant. In urban areas, where public transport is a key part of daily life, the shift to teleportation could lead to a significant reduction in ridership, potentially forcing cities to rethink their transportation infrastructure entirely. Freight companies that move goods by land, sea, or air would struggle to stay relevant. Trucking, air freight, and rail cargo would become unnecessary, as products could be teleported directly from manufacturers to consumers. The ripple effects of this disruption would impact countless jobs and businesses that depend on these industries. Tourism could be reshaped entirely. The ability to teleport could lead to a boom in tourism, as people would be able to visit far-off destinations on a whim. However, this influx of visitors could strain popular tourist spots, leading to overcrowding and putting pressure on local economies and ecosystems. Manufacturing industries might need to adjust to the new realities of teleportation. With goods able to be instantly transported, the entire concept of local versus international manufacturing could shift. Companies might centralize production, knowing that their products can be teleported anywhere instantly, impacting global manufacturing hubs. The real estate industry could also be disrupted. The demand for housing near workplaces or city centers could diminish as people no longer need to live close to their jobs. This could lead to shifts in housing prices and a re-evaluation of what constitutes desirable locations for living. The energy sector might see shifts too. While teleportation could reduce the need for fossil fuels in transportation, the immense energy requirements for teleportation itself could lead to increased demand for alternative energy sources. This could spur growth in clean energy industries while challenging traditional energy companies. Overall, teleportation would cause widespread disruption across multiple industries, forcing businesses to either adapt or face extinction. The speed and scale of this change would reshape the global economy, altering the way we work, travel, and consume goods, with both positive and negative consequences. A borderless world enabled by teleportation would profoundly change the way cultures interact and evolve. Instant travel between countries would blur the lines between distinct national identities, as people from different parts of the world could easily mix, creating a more interconnected global culture. Cultural exchange would accelerate, with ideas, traditions, and customs spreading rapidly across the globe. While this could lead to greater understanding and appreciation of diverse cultures, it might also lead to the erosion of regional uniqueness as global trends overshadow local traditions. Languages could evolve more quickly in a world where people move freely across borders. While this could foster linguistic diversity in some areas, it could also push dominant languages, like English, to spread even further, potentially threatening smaller or indigenous languages. Art and entertainment would likely become more globalized as well. Teleportation would allow artists, performers, and creators to easily share their work with international audiences, leading to new collaborations and cultural fusions. However, it might also make it harder for regional art scenes to maintain their individuality. Food cultures, traditionally tied to specific regions, could spread and evolve at an unprecedented pace. Dishes and ingredients from one country could instantly appear on the other side of the world, making global cuisines even more accessible. While this could enrich culinary diversity, it might also dilute the distinctiveness of local food traditions. Cultural identity could shift as people no longer feel tied to a specific place. National and regional identities might become less important as people move freely between locations, leading to new forms of identity based on global citizenship rather than local ties. Religious practices, too, could change in a borderless world. Pilgrimages to sacred sites, for instance, would become easier, leading to more frequent and diverse participation in spiritual traditions. However, the ease of movement might also challenge the meaning and significance of such journeys. The concept of community might transform as well, with people able to maintain relationships across vast distances. Local communities might become less central to daily life. Instead, people could form global networks of like-minded individuals, altering the way we think about social ties and support systems. Cultural festivals and events, once rooted in specific places, could become more international in nature. Teleportation would allow people from all over the world to attend events that were once geographically restricted, turning local celebrations into global gatherings. Fashion and clothing styles could evolve more rapidly, with global trends spreading instantly through teleportation. Traditional clothing might blend with modern designs as people adopt new styles from different cultures, leading to a constantly shifting global fashion landscape. Education systems would also be impacted. Students could attend schools or universities anywhere in the world, fostering a more globalized approach to learning. However, this could create challenges for preserving local histories, languages, and cultural practices in educational curricula. Ultimately, teleportation's ability to erase borders would create a more interconnected world, but it could also challenge the preservation of cultural identities. As people and ideas move freely across the globe, the balance between global unity and cultural diversity would become a central question for societies to navigate. Teleportation has the potential to either unify or divide society in profound ways. On one hand, the ability to travel instantly could foster greater global connection, making it easier for people from different backgrounds to meet, collaborate, and share experiences. This could lead to increased understanding and a stronger sense of global unity. On the other hand, teleportation could deepen divisions, especially if access to the technology is limited. If only the wealthy or powerful can afford to teleport, it might create a new class divide, with those who have access able to move freely, and those without left behind, restricted to traditional means of travel. Instant access to different regions of the world could reduce the significance of national boundaries, encouraging a more inclusive and interconnected society. People might begin to identify less with their country or region and more with a global community, leading to new forms of social cohesion. However, the ease of teleportation could also exacerbate inequality. If some regions or communities are left out of the teleportation network, they could become isolated and disadvantaged. This might lead to resentment and social unrest, as those with access to teleportation enjoy privileges unavailable to others. Teleportation could unify families and communities that have been separated by distance, allowing people to visit loved ones instantly and regularly. This could strengthen personal relationships and reduce the emotional strain of being far apart, helping to bring people closer together. Yet it might also create social fragmentation. With the ability to teleport anywhere, people might become less rooted in their local communities, leading to a weakening of neighborhood bonds. Physical proximity has traditionally fostered community, and teleportation could undermine that, encouraging more transient relationships. The technology could open doors to unprecedented collaboration across borders. Researchers, artists, and professionals could easily gather from all over the world, accelerating innovation and cultural exchange. This could create a sense of global solidarity as people work together to solve shared challenges. But teleportation could also lead to new forms of competition. Countries or corporations that control teleportation infrastructure might wield disproportionate power, leading to geopolitical conflicts. Control over who can teleport and where could become a source of tension, dividing nations and communities. Education might become more global, with students able to attend the best schools and universities from anywhere. This could create a more unified educational experience, with knowledge and ideas flowing freely across cultures, helping to foster a more informed and cohesive society. At the same time, teleportation could drive divisions within education. If access to elite institutions is determined by the ability to teleport, those without access could be left at a disadvantage, deepening educational inequality and limiting social mobility. In terms of work, teleportation could unite the global workforce, allowing people to live in one part of the world while working in another. This could create new opportunities for collaboration and economic growth, connecting people and ideas in ways that were previously impossible. However, it could also divide labor markets. Workers in regions without access to teleportation could be excluded from high-paying jobs, further widening the gap between rich and poor. Whether teleportation unifies or divides society will depend largely on how it's implemented and who has access to this transformative technology. Government-funded teleportation research could play a critical role in advancing the technology and ensuring that it serves the public interest. By investing in teleportation, governments could push the boundaries of science and unlock new possibilities in transportation, communication, and national security. One of the main reasons for government involvement is to ensure that teleportation research is conducted responsibly and ethically. Left solely to private companies, the technology could be developed in ways that prioritize profit over public safety or accessibility. Government funding could help maintain a balance between innovation and regulation. Another benefit of government-backed research is the potential to make teleportation available to a wider segment of society. Without government support, teleportation technology might remain exclusive to the wealthy or large corporations. Public funding could help democratize access to teleportation, making it a tool for everyone, not just a privileged few. National security is also a key consideration for governments. Teleportation could revolutionize defense strategies, allowing for instant deployment of troops or equipment. Government-funded research would ensure that nations are prepared to integrate teleportation into their security infrastructure while preventing the technology from falling into the wrong hands. Governments could also use teleportation to address global challenges such as climate change. By reducing the need for traditional transportation, teleportation could cut down on carbon emissions and help create a more sustainable future. Government investment in this technology could ensure that environmental considerations remain a priority. Another reason for government involvement is to establish international standards and regulations. Teleportation, if left unregulated, could lead to a range of issues, from privacy violations to illegal activity. Government research could help shape the legal frameworks needed to manage the risks and ethical dilemmas posed by teleportation. Publicly funded research could also lead to advancements in other areas of science. Teleportation experiments often overlap with fields like quantum mechanics, computing, and material science. By investing in teleportation, governments could drive progress across a range of scientific disciplines, leading to broader technological breakthroughs. There's also the potential for economic benefits. Government investment in teleportation could create new industries, jobs, and markets. By leading the way in teleportation research, countries could position themselves as global leaders in this emerging field, attracting investment and talent from around the world. Collaboration between governments and academic institutions could foster innovation. Universities conducting research with public funding would have the resources and freedom to explore new ideas without the constraints of corporate interests. This could lead to breakthroughs that might not emerge from private sector efforts alone. Governments could also use teleportation to enhance public services. From healthcare to emergency response, instant transportation could revolutionize how governments provide aid to their citizens. Government-funded research could ensure that teleportation technology is developed in a way that prioritizes public welfare. Another reason for government involvement is to promote transparency in the development of teleportation technology. When research is publicly funded, there's a greater level of accountability, ensuring that the public is informed about the potential risks and benefits. This transparency is crucial for maintaining public trust. In the end, government-funded teleportation research could ensure that the technology develops in a way that benefits society as a whole. By investing in responsible, ethical, and transparent research, governments can help shape the future of teleportation to meet public needs and address global challenges. The private sector is likely to play a significant role in the development of teleportation technology. Companies with deep pockets and a willingness to take risks could drive innovation in ways that government-funded research might not be able to. The race to commercialize teleportation could spark rapid advancements. Private companies often move faster than government-funded programs. Without the bureaucratic hurdles of public institutions, the private sector can be more agile, quickly testing new ideas and technologies. This speed could accelerate progress toward making teleportation a reality. Venture capitalists and tech giants are always looking for the next big thing. As teleportation research advances, private investors may see it as an opportunity to disrupt industries like transportation, logistics, and even real estate. The potential financial returns could be enormous, motivating companies to pour resources into teleportation R&D. Companies in industries like shipping and transportation stand to benefit the most from teleportation. By investing in the technology, they could revolutionize the way goods and people are moved, potentially saving billions in costs and opening new markets. The private sector's focus on profitability could drive teleportation forward. Tech companies, especially those focused on quantum computing or artificial intelligence, are already making strides in the areas necessary for teleportation. These fields are essential for the development of the technology, and companies at the forefront of these industries are well positioned to make breakthroughs that bring teleportation closer to reality. One of the risks of private sector involvement, however, is the potential for monopolization. If a few companies gain control over teleportation technology, they could dominate entire sectors of the economy. This could limit access to teleportation, making it a privilege for the wealthy or large corporations while leaving others behind. There's also the possibility that the private sector's focus on profit could lead to cutting corners in terms of safety. Teleportation, especially in its early stages, will require extensive testing and regulation to ensure it's safe for public use. Companies eager to bring the technology to market might overlook some of these concerns. Collaboration between private companies and governments could help mitigate these risks. By working together, the private sector could bring its innovation and speed, while the public sector ensures that teleportation technology is developed safely, ethically, and in a way that benefits society as a whole. Intellectual property will likely become a major issue as companies race to develop teleportation technology. Patents and proprietary research could create legal battles over who owns the technology and who can profit from it. This could slow down progress if companies become more focused on protecting their interests than advancing the technology itself. The private sector's ability to fund large-scale projects will be critical in teleportation's development. Companies with the financial resources to invest in long-term research and development could push teleportation from theory to practice, especially as breakthroughs in related fields continue to emerge. Consumer demand could also drive private sector involvement. If teleportation becomes a possibility, there will likely be enormous demand for the convenience and efficiency it offers. Companies that can meet this demand will be positioned to profit massively, pushing them to invest heavily in making the technology viable. In the end, private sector advancements could be the key to making teleportation a reality. While governments and academic institutions provide the foundation for research, the private sector's resources, speed, and competitive drive will likely play a major role in turning the dream of teleportation into a practical, everyday technology. Space agencies around the world are deeply interested in teleportation, as it could revolutionize space exploration. The ability to instantly transport materials or astronauts between planets or spacecraft would solve one of the biggest challenges in space travel: the vast distances and time required to reach distant locations. For agencies like NASA, teleportation could dramatically reduce the costs associated with space missions. Current missions rely on heavy, expensive rockets to transport equipment and crew to space. Teleportation would eliminate the need for these rockets, making space exploration more efficient and affordable. One of the most compelling reasons for space agencies to explore teleportation is the potential to improve astronaut safety. Teleporting crew members between a spacecraft and a base on another planet could reduce the dangers associated with space travel, such as radiation exposure or the risks of long-duration missions. Teleportation could also solve the logistical challenges of transporting supplies to astronauts on long missions. Rather than sending multiple resupply missions, space agencies could instantly teleport food, water, and equipment directly to spacecraft or planetary bases, ensuring astronauts have everything they need without delays. The exploration of distant planets and moons would become much more feasible with teleportation. Space agencies could deploy robots or even humans to Mars, Europa, or beyond, without the long travel times currently required. This would open up entirely new opportunities for scientific discovery and exploration. Teleportation could also support the construction of off-world colonies. Transporting building materials, habitats, and other infrastructure could be done instantly, making it easier to establish a sustainable human presence on other planets. Space agencies could collaborate with private companies to build entire cities in space. Collaborations between space agencies could accelerate progress. By pooling resources and knowledge, agencies like NASA, ESA, and Roscosmos could work together to overcome the scientific and technical challenges of teleportation, sharing breakthroughs and minimizing costs in the process. The idea of teleporting data or samples back to Earth could also transform how space missions are conducted. Space agencies could send rovers or probes to gather samples on distant planets and then instantly teleport the data or small samples back to Earth for analysis, speeding up scientific research. Teleportation might also be a solution to some of the physical limitations of human space travel. Current technology cannot transport astronauts beyond the inner solar system in a reasonable amount of time. With teleportation, space agencies could explore further into the galaxy, sending humans to places that are currently out of reach. Space tourism could benefit from teleportation as well. Agencies working with commercial space companies could offer teleportation as a service to take tourists to space stations or the moon. This would open up space travel to a much larger audience, potentially making it a more common experience for people on Earth. Ethical considerations would be important for space agencies to address. Teleportation raises questions about the effects on astronauts' health, the implications of duplicating or destroying individuals during transport, and how to manage the technology responsibly. Space agencies would need to lead the way in setting ethical standards for its use. Ultimately, space agencies' interest in teleportation reflects their desire to push the boundaries of human exploration. Teleportation has the potential to unlock new frontiers, allowing humanity to explore space in ways that were once unimaginable. By investing in this technology, space agencies could usher in a new era of space travel. Universities and academic institutions are vital to advancing teleportation research. These institutions provide the foundational knowledge and theoretical frameworks needed to explore the complex science behind teleportation, particularly in quantum mechanics and physics. Their work often lays the groundwork for future breakthroughs. In academic settings, researchers can pursue long-term, curiosity-driven projects that might not immediately yield profitable results, but are crucial for pushing the boundaries of what's possible. Teleportation is one of those fields where universities can invest time and resources into understanding the fundamental science without the pressure of immediate commercialization. Collaboration is key in university research. Academics from different disciplines, including physics, computer science, and engineering, can work together on the various challenges of teleportation. This interdisciplinary approach allows universities to explore the full scope of teleportation, from the technical hurdles to the ethical and philosophical questions it raises. Universities also have access to cutting-edge technology and laboratories, making them ideal places for experimentation. Quantum computing, which plays a critical role in teleportation research, is often advanced in academic settings where researchers can develop and test new algorithms and systems that could make teleportation possible. Academic conferences provide a forum for sharing breakthroughs and fostering collaboration between researchers. These gatherings allow scientists from universities around the world to exchange ideas, present their findings, and inspire new approaches to solving the challenges of teleportation. Universities are also essential in training the next generation of scientists and engineers who will continue to develop teleportation technology. Graduate students and postdoctoral researchers often work on the most cutting-edge projects, gaining the skills and knowledge needed to carry this research forward into the future. One of the key roles of academic institutions is in exploring the ethical implications of teleportation. Universities are places where scholars can debate and analyze the moral questions surrounding this technology, from issues of identity and continuity to the societal impact of instant travel. Funding for university-led teleportation research often comes from government grants or private foundations. This support allows academic researchers to pursue innovative ideas and conduct long-term studies that might be too risky or costly for private industry to undertake. In addition to government funding, partnerships between universities and private companies can drive teleportation research forward. These collaborations allow academic researchers to apply their theoretical knowledge to real-world problems, while companies benefit from the cutting-edge innovations being developed in university labs. Universities are also responsible for publishing peer-reviewed papers that contribute to the global body of knowledge on teleportation. These papers provide critical insights into the progress being made, ensuring that research is transparent, rigorously tested, and available for others to build upon. The role of universities isn't just limited to scientific research. Academic institutions also play a role in educating the public about teleportation. Through lectures, publications, and public outreach, universities help explain the science behind this technology and address common misconceptions. Ultimately, universities and academic research are the backbone of teleportation's scientific progress. Their focus on fundamental research, ethical considerations, and interdisciplinary collaboration makes them indispensable in the journey toward making teleportation a reality. Collaboration between sectors will be essential in developing teleportation technology. Governments, private companies, and academic institutions each bring unique strengths to the table, and working together could accelerate progress in ways that none of these sectors could achieve alone. Governments can provide funding and set regulations to ensure that teleportation research is conducted responsibly. Meanwhile, private companies have the resources and drive to push for commercialization, turning theoretical research into practical applications. Academia plays a critical role in providing the scientific foundation for teleportation. Universities and research institutions conduct the long-term, experimental studies necessary to explore the fundamental principles behind quantum mechanics and information transfer. Private sector partnerships with universities could fuel faster breakthroughs. Companies could offer advanced equipment and funding for research, while universities provide the expertise and experimental rigor needed to tackle the scientific challenges of teleportation. Public-private partnerships could be essential for balancing innovation with regulation. Governments can ensure that teleportation technology is developed with public safety in mind, while private companies focus on making it commercially viable. This balance could help prevent the risks of unregulated technological development. Collaboration could also address the ethical concerns associated with teleportation. Academic institutions, alongside government bodies, can develop ethical frameworks for the use of teleportation technology, ensuring that its implementation is responsible and fair. Space agencies might collaborate with tech companies and academic researchers to apply teleportation technology to space exploration. These partnerships could combine resources and expertise, enabling breakthroughs that push human exploration further than ever before. Cross-sector collaboration is crucial for solving the energy challenges of teleportation. Governments could fund energy research while the private sector works on scalable solutions. Academic researchers can test theories and find ways to minimize energy consumption during the teleportation process. International collaboration could be just as important. Countries working together on teleportation research could share knowledge, reduce duplication of effort, and ensure that the technology benefits people around the world, rather than being limited to a few powerful nations. There's also the potential for collaboration on infrastructure. Building the necessary networks and facilities for teleportation will require expertise from the transportation, telecommunications, and energy sectors. Working together, these industries could create the systems needed to support teleportation on a global scale. Joint ventures between space agencies and commercial enterprises could bring teleportation closer to becoming a practical tool for space travel. Space missions often require significant resources, and collaboration could help distribute costs while driving innovation. Ultimately, successful collaboration between sectors will determine how quickly teleportation becomes a reality. By pooling resources, knowledge, and expertise, governments, companies, and universities can overcome the many scientific and practical challenges involved in bringing teleportation from science fiction into our daily lives. In this video, we explored the fascinating world of teleportation, from its early mentions in literature to the cutting-edge science that may one day make it a reality. We began by looking at how teleportation has captured our imagination, appearing in countless books, movies, and TV shows, shaping public perception of what could be possible. Fiction has always been a driving force in inspiring scientific inquiry, and teleportation is no exception. We then delved into the science behind teleportation, starting with quantum mechanics and quantum entanglement. While the concept of instant travel across vast distances sounds far-fetched, quantum experiments have already shown that information can be teleported at the subatomic level. Scaling that up to humans, however, introduces challenges in data complexity and energy requirements that are far beyond our current capabilities. The ethical and philosophical questions around teleportation were also discussed. From the destruction and duplication of matter to the continuity of self, teleportation presents profound dilemmas about identity and existence. We examined how these issues would need to be addressed before teleportation could become a viable technology, ensuring it is developed responsibly. We also covered the potential societal impacts of teleportation. Instant travel could unite or divide society, offering new opportunities for global collaboration while also deepening inequality if access to the technology is not widespread. Teleportation would fundamentally change how we think about borders, travel, and community, creating a borderless world that challenges existing norms. In terms of practical implications, we looked at how teleportation could disrupt industries, from transportation and shipping to tourism and energy. The ripple effects of this technology could completely reshape economies, alter the workforce, and demand new infrastructure. Companies and governments would need to adapt to the new reality that teleportation could bring. Government-funded research, private sector advancements, and the role of universities all play crucial parts in the development of teleportation technology. Collaboration across these sectors will be essential to overcoming the scientific, ethical, and logistical hurdles that teleportation presents. We also discussed how space agencies see teleportation as a potential game-changer for space exploration. From entertainment's impact on science to the academic research that lays the groundwork for teleportation, we've seen how interconnected the journey toward teleportation truly is. Each sector, whether government, private, or academic, brings something important to the table, and working together is the only way to make teleportation more than a distant dream. We also touched on how teleportation could transform international relations and politics. With teleportation removing physical barriers, governments would need to rethink security, trade, and even the concept of national sovereignty. The political landscape would shift in unpredictable ways, making this technology not just a scientific breakthrough, but a global event. As teleportation research progresses, we'll need to carefully balance its potential with the challenges it introduces. Ensuring that teleportation is safe, ethical, and accessible will be critical in making it a positive force in the world. The path ahead is uncertain, but the possibilities are truly exciting. If you enjoyed this deep dive into teleportation and want to see more videos on future technologies and their impact on society, be sure to like this video and subscribe to the channel. Don't forget to check out our other videos for more fascinating topics, and join us as we continue to explore the technologies that will shape our future. Thank you for watching.